As we journey back across the unfathomable depths of time, we arrive at a moment both catastrophic and transformative. A juncture in Earth's deep history, known today as the Permian-Triassic boundary, occurring approximately 252 million years ago. This epical moment marks the most devastating biological crisis our planet has known: the Great Dying. It stands as the most severe mass extinction event in Earth's history, wiping out an estimated 90 to 96% of marine species and around 70% of terrestrial vertebrate species. The scale and intensity of this extinction event were breathtaking, a cataclysm that drastically reset the evolutionary stage and forged the framework for an entirely new biological era to emerge, the Triassic. To comprehend the profound changes that unfolded after the Great Dying, it's essential to grasp the environmental and ecological devastation that the event unleashed. The Permian period that preceded it was a time of vast supercontinents, culminating in Pangaea, a supercontinent that tightly clustered nearly all land masses together. This immense landmass contributed to extreme climatic volatility, including scorching aridity in the continental interiors and harsh seasonal extremes. Such conditions made ecosystems inherently fragile even before catastrophe struck. The trigger mechanisms of the Great Dying remain subjects of active research, but a confluence of events likely played pivotal roles. Siberian volcanic eruptions unleashed massive flood basalts, releasing enormous volumes of greenhouse gases such as carbon dioxide, methane, and sulfur dioxide into the atmosphere. This volcanic activity seriously disrupted global climate systems, causing rapid warming, ocean acidification, and widespread anoxia, a depletion of oxygen in ocean waters. These conditions decimated marine life, from shallow reefs to the deep ocean, and dramatically altered terrestrial habitats. The aftermath of this extinction event painted a grim and barren world. Vast swathes of the marine realm were lifeless, while on land, many dominant groups, including various amphibians, large synapsids, and ancient reptilian species, vanished. Forests were decimated, exposing barren soil and heightening erosion. The air quality itself was likely toxic due to lingering volcanic gases and ash. However, from this devastation, the seedbed for renewal was sown. The Earth's crust began gradually stabilizing, and climatic systems entered a phase of nascent recovery. The global atmosphere, though still volatile, started to clear as volcanic activity waned. Persistent greenhouse gases kept temperatures elevated, but the extreme swings began to moderate over time. The oceans, too, slowly regained their oxygenation and life-supporting capacity. In these recovering environments, a tantalizing question arises: how did life find its footing again? Which lineages were poised to survive the harsh Triassic landscapes and reshape biological communities? The stark reality is that the Great Dying reset evolutionary clocks, eradicating many established groups but creating vast ecological vacancies. This effectively eliminated dominant competitors, paving the way for the rise of new organisms better adapted to the new environmental regime. The stage was set for the emergence of archosaurs, a diverse group of reptiles that included the ancestors of both crocodilians and dinosaurs. These creatures were particularly well poised to fill the void. Their more efficient respiratory and cardiovascular systems, along with other anatomical innovations, gave them a resilience that enabled exploitation of recovering niches. In the aftermath of the extinction, archosaurs began radiating, diversifying into forms that would eventually dominate terrestrial ecosystems. Simultaneously, flora underwent dramatic shifts. Triassic landscapes started to be recolonized by hardy pioneer plants. Early gymnosperms, such as conifers and seed ferns, became prevalent, providing the fundamental architecture for terrestrial ecosystems. These plants had the evolutionary advantage of seeds, encased embryos that protected the next generation against harsh conditions, a critical innovation in disturbed landscapes. The recovery of aquatic ecosystems was equally fascinating. The re-establishment of reef systems, the return of marine invertebrate diversity, and the gradual repopulation of fish laid the foundation for future Mesozoic seas. The oceans began to support communities increasingly complex in structure and function, though the full diversity would take millions of years to return. Geologically, the Triassic was a time of continued tectonic activity. Pangaea's configuration contributed to distinct climate zones, from arid interiors to more humid coastal regions. These physical dynamics encouraged the diversification of life both on land and in the water. The land was marked by extensive dune fields right alongside lush fluvial river systems and lakes, creating a patchwork of habitats rich in ecological opportunity. Importantly, the Triassic period was not a simple continuum of recovery, but a dynamic epoch characterized by fluctuating conditions. Episodes of climate instability, including bouts of humidity and drought, shaped the evolutionary pathways of resident organisms. These environmental oscillations served as selective pressures accelerating the innovation and adaptation that defined much of Triassic life. In weaving together this tapestry of post-extinction Earth, a portrayal emerges of a planet struggling yet resilient. Life did not merely survive. It began to innovate and experiment with new forms and strategies to thrive in an altered world. The Triassic's foundation was laid in this crucible of disturbance and renewal, a world starkly different from what had preceded it, yet fertile ground for the rise of the first dinosaurs and their contemporaries. So, as we begin to explore the intricacies of the Triassic era, it's essential to recognize that every lush forest or predator-prey interaction of this age was shaped by a profound legacy of devastation. The Great Dying was more than an end. It was a doorway, ushering in a new chapter of Earth's biological history, filled with fresh challenges and opportunities. The evolutionary drama unfolding next would set in motion forces that would transform life forever, culminating in the age of dinosaurs. In the upcoming chapters, we will delve deeper into how ecosystems rebuilt themselves after such turmoil, tracing the renewal of flora, fauna, and climate systems. We will learn how early reptiles and other pioneers navigated these challenging landscapes, and how this crucible gave birth to the early dinosaurs, the protagonists of a dynamic, evolving world. Together, we will witness the subtle, persistent forces sustaining Earth's pulse as it slowly rose from near extinction and ventured into a new age of diversity and complexity. Following the cataclysmic upheaval of the Great Dying, Earth found itself in a state of desolation, yet imbued with the latent potential for recovery. As the Triassic period unfolded, life began to reclaim its territory in a delicate, gradual process of ecosystem rebirth. An evolutionary renaissance characterized by intertwined recoveries of flora, fauna, and climate systems. This delicate dance between biological resurgence and environmental stabilization shaped the trajectory of life on Earth, setting the stage for the rise of complex ecosystems that would eventually nurture the dawn of the dinosaurs. To understand this remarkable recovery, we must first appreciate the vast scale of devastation left behind. Marine environments were essentially reduced to microbial mats and barren floors, while terrestrial landscapes bore the scars of deforestation, soil erosion, and the almost complete loss of large vertebrates. This vacuum, however dire, created opportunities for new groups of organisms to emerge and diversify. On land, the revival of flora was among the first visible signs of ecological resurgence. Pioneer plants, especially drought-tolerant gymnosperms such as seed ferns, pteridosperms, conifers, and cycads, started repopulating landscapes. These plants were remarkably well adapted to the harsh Triassic environments. Unlike spore-reliant plants such as ferns and mosses, gymnosperms produced seeds, tiny packets containing embryos protected by a tough coat, capable of withstanding dry, nutrient-poor conditions. This evolutionary innovation was fundamental in sustaining the earliest ecosystems of the Triassic. Fossil evidence reveals that the early Triassic flora often consisted of assemblages dominated by these hardy seed plants, interspersed with lycopsids, club mosses, and other groups that had survived the extinction. These plants recolonized disturbed soils, stabilizing landscapes and initiating ecological succession. Over time, more complex forests began to emerge, providing habitats and food sources for terrestrial herbivores. Climate during this recovery phase played a dynamic yet pivotal role. Though globally still affected by lingering greenhouse gases from the Permian volcanism, the Earth's atmosphere began to stabilize. The late early Triassic climate was generally hot and arid, especially in the interior regions of supercontinent Pangaea, where vast desert-like conditions dominated. Seasonal patterns brought occasional monsoonal rains, creating patchy environments of wet river valleys amid expansive drylands. This heterogeneity in climate and habitat availability fostered evolutionary experimentation. Some regions witnessed dry conditions that favored drought-resistant flora and associated fauna, while others supported more humid ecosystems capable of sustaining diverse life. These varying microhabitats allowed flora and fauna to find ecological niches tailored to their survival strategies. In the oceans, recovery lagged slightly behind terrestrial resurgence, but followed a similar upward trajectory. The Great Dying had decimated marine biodiversity, reducing ecosystems to simple, low-diversity communities for millions of years. During the early Triassic, seas were dominated by microbial communities and opportunistic species like certain bivalves and gastropods, which flourished in oxygen-poor conditions. As oxygen levels gradually rose and water chemistry improved, coral reefs began to reappear, marking a critical moment of ecological complexity. While early Triassic reefs were typically dominated by sponges and algae, they paved the path for more diverse reef-building organisms in the Middle and Late Triassic. Marine ecosystems diversified to include ammonoids, infecting nectonic, swimming lifestyles, echinoderms such as sea urchins and starfish, and a growing variety of fish and marine reptiles, including early ichthyosaurs and nothosaurs. A fascinating aspect of the Triassic rebirth was the gradual restructuring of food webs. In marine systems, the simplicity of post-extinction communities meant that predator-prey dynamics were initially basic. Over time, the return of larger predatory fishes and reptiles introduced complex interactions, heralding an arms race in adaptations and survival strategies that would continue through the Mesozoic. On terrestrial landscapes, similar restructuring unfolded. The disappearance of dominant Permian synapsids, mammal-like reptiles once occupying top predator roles, left vacuums rapidly filled by new archosaurian groups. These early archosaurs diversified into a variety of forms, some terrestrial, others semi-aquatic, exploiting emerging niches ranging from herbivory to carnivory. Another hallmark of post-extinction ecosystems was the expansion of early amphibians and smaller tetrapods. While many Permian amphibian lineages were lost, some persisted and adapted to the new environmental realities. These include temnospondyls, large amphibians surviving in wetter areas, and early members of the ancestral lineages leading to mammals, although mammaliforms themselves would arise later. Their presence, along with the burgeoning diversity of reptiles, contributed to increasingly complex terrestrial trophic structures. A critical thread weaving through this recovery was the establishment of symbiotic relationships and ecological interdependencies. Fungi, bacteria, and primitive lichens played essential roles in soil formation and nutrient cycling, facilitating plant colonization and stabilizing ecosystems. The underground microbial world, often invisible in the fossil record, was foundational for above-ground renewal. At the same time, evolutionary pressures induced gradual adaptive radiations. Species developed traits enhancing desiccation tolerance, high metabolic efficiency, improved locomotion, or more effective reproductive strategies. These subtle innovations would resonate through the Triassic and beyond. Looking deeper, the patterns of recovery were spatially heterogeneous. Some regions show rapid diversification and return to pre-extinction biodiversity levels, while others reflect prolonged impoverishment. This mosaic recovery reflects complex interactions between local climate, geography, and biotic factors. By the Middle Triassic, roughly 240 million years ago, ecosystems exhibited substantial restoration and increased complexity. Diverse conifer-dominated forests blanketed parts of Pangaea, wetlands expanded, and aquatic systems hosted a variety of vertebrates and invertebrates. This biological vitality marked a turning point in Earth's history, moving from fragile recovery to an era of expansive diversification. These developing ecosystems also laid groundwork for intense biotic interactions. The emergence of new herbivorous species pressed plants to evolve defenses like tougher leaves or chemicals, setting off co-evolutionary battles. Predators and prey engaged in escalating contests, refining sensory abilities, speed, and weaponry. In conclusion, the rebirth of ecosystems in the Triassic was a testament to life's resilience. Through cycles of adversity and adaptation, flora and fauna reclaimed their realms amid changing climates and shifting landscapes. This process was neither swift nor linear, but featured gradual improvements interspersed with episodes of instability. As we continue our exploration, the unfolding story of archosaur ascendance and the first stirrings of dinosaur lineage will become clearer. Understanding how early Triassic life navigated this renewal offers valuable insights into the foundations and dynamics of ecosystems, lessons echoing across millennia to the present day. In the intricate mosaic of the Triassic period, amid the slow but steady recovery of life from the darkest clouds of the Great Dying, a remarkable evolutionary narrative unfolded, one that would ultimately lay the groundwork for the rise of dinosaurs and reshape terrestrial ecosystems forever. This narrative is the story of archosaur ascendancy. Archosaurs, often described as the ruling reptiles, were a broad and diverse clade that rose to dominance as pre-dinosaur predators in the Triassic landscape, carving out new ecological roles while competing fiercely with other reptilian groups. But who were these archosaurs, and why did they come to hold such a pivotal role in the evolutionary drama of this era? The term archosaur means ruling lizards and refers to a group of diapsid reptiles that trace their origins back to the late Permian or early Triassic. Archosaurs include not only the ancestors of dinosaurs, but also the relatives of modern crocodilians and other extinct forms. Their evolutionary significance lies deeply in their anatomical and physiological innovations, which distinguished them from other reptile lineages during a time of profound ecological turnover. In the direct aftermath of the Permian-Triassic mass extinction, many ecological niches were vacated, particularly those occupied by dominant amphibians and synapsid predators. Archosaurs seized these openings with notable success. Early in the Triassic, archosaurs diversified into multiple groups displaying a variety of forms, ranging from agile bipedal hunters to armored quadrupeds. Among the earliest archosaurs were the Rauisuchians. These were formidable, top-level predators that often reached impressive sizes, some up to 6 meters or more in length. Rhynchosaurs possessed massive skulls equipped with blade-like, serrated teeth, reminiscent of later theropod dinosaurs, designed for slicing flesh. Their limbs were positioned under the body rather than sprawling sideways, allowing for greater mobility and stamina, an evolutionary leap improving locomotion efficiency. Fossil evidence shows they ruled the open landscapes and riverine environments, exerting predatory pressure on other reptiles and early herbivores. Alongside Rhynchosaurs, another major lineage, the aetosaurs emerged as dominant herbivores. Though armored with bony plates resembling crocodile osteoderms, these quadrupeds grazed on low vegetation, filling an herbivorous niche essential for ecosystem functioning. The presence of such herbivores provided a stable energy flow within food webs and supported the carnivorous archosaurs, a quintessential example of ecosystem rebuilding through interdependent species. Additionally, phytosaurs, superficially similar to modern crocodiles but evolutionarily distinct, prowled the rivers and swamps. These semi-aquatic archosaurs had long snouts filled with numerous sharp teeth, adapted for fish catching and opportunistic predation alike. Their crocodile-like appearance is a striking example of convergent evolution. Two unrelated groups evolving similar features to thrive in similar environments. What set archosaurs apart were physiological traits that conferred competitive advantages. Notably, archosaurs had a more advanced respiratory system, with a combination of unidirectional airflow through their lungs, similar to modern birds, allowing efficient oxygen extraction even in hot or low oxygen conditions that characterized early Triassic climates. This respiratory efficiency supported high metabolic rates and sustained activity levels, enabling these reptiles to pursue prey or forage over long distances, unlike many contemporaries who were more limited in stamina. Their limb posture, often erect or semi-erect, reduced energy expenditure during locomotion by supporting the body above the ground, a significant improvement over sprawling gait. This arrangement allowed better endurance, speed, and more complex movement patterns such as bipedalism, which later became a hallmark of true dinosaurs. Sensory adaptations also bolstered archosaur success. Many had well-developed binocular vision aiding depth perception, critical for hunting and environmental awareness. Enhanced auditory systems further refined their capacity to detect prey or danger. Together, these faculties shaped archosaurs into apex hunters and capable foragers, able to occupy a variety of ecological niches. Ecologically, the archosaurs did not evolve in isolation. Their proliferation impacted and was influenced by interactions with other groups. Early synapsids, the so-called mammal-like reptiles, while diminished by the Great Dying, persisted in smaller, more specialized forms. Early amphibians and diverse small reptiles continued to inhabit wetter ecosystems or refugia. Competition, predation, and changing environmental conditions drove evolutionary pressures that shaped behaviors and morphology across taxa. Intriguingly, the relative dominance of Rhynchosaurs and other archosaurs was not without intermittent challenges. Several large predatory amphibians and specialized synapsids coexisted for varying durations throughout the early and middle Triassic, reminding us that ecological landscapes were complex, consisting of fluctuating competitive balances rather than simple linear successions. Yet, the adaptive flexibility and evolutionary innovations of archosaurs proved decisive, allowing them to outlast and outcompete many rivals. The fossil record from Upper Triassic localities across Pangaea provides a vivid window into this archosaur reign. Sites such as the Chinle Formation in the southwestern United States, the Ishigualasto Formation in Argentina, and the Germanic Basin of Europe reveal a rich diversity of archosaur species. These fossils portray a vibrant ecosystem mosaic, where nimble predators stalked conifer forests and amphibious hunters lurked in waterways, interacting with a diversity of herbivorous reptiles, plants, and smaller creatures. Importantly, it was within this framework of archosaur prominence that the first true dinosaurs began emerging. The Triassic archosaur lineage was not singular, but a sprawling family tree branching into varied evolutionary experiments. Dinosaurs would later distinguish themselves through their unique anatomical modifications, but their early ancestors shared the stage with their archosaur cousins, competitors and allies alike. The ascendancy of archosaurs thus represents a crucial transitional phase in evolution. It was a dynamic time of adaptation, competition, and innovation, setting a precedent for the later explosive diversification seen in the Jurassic and Cretaceous periods. Understanding this period deepens our appreciation of how early archosaurs, as pre-dinosaur predators, established ecological architectures that would nurture the rise of perhaps the most iconic creatures in Earth's history. As we proceed, we will explore the diversity of early herbivores and lesser-known reptilian forms that thrived in the Triassic, further enriching the tapestry of life during this remarkable epoch of renewal and change. Following the marked ascendancy of archosaurian predators in the Triassic, the ecosystems of this transformative era witnessed not only carnivorous dominance, but also a remarkable diversification of herbivorous reptiles, whose evolution played a fundamental role in structuring the food webs and fostering ecological complexity. Among the most significant herbivorous groups that flourished during this time were the rhynchosaurs, a uniquely adapted and successful clade whose rise intricately illustrates the interplay of evolutionary innovation, environmental opportunity, and competitive dynamics in the aftermath of the Permian mass extinction. Rhynchosaurs first appeared early in the Triassic and quickly radiated into a variety of species that thrived until their eventual decline by the end of the Triassic. Their evolutionary success sprang from a suite of specializations that allowed them to exploit plant resources effectively in a world that was still recovering and changing rapidly. Notably, rhynchosaurs developed powerful beak-like jaws equipped with continuously replacing teeth arranged in broad, grinding surfaces ideal for shearing and processing tough Triassic vegetation. The anatomical configuration of rhynchosaurs was quite distinctive. Their skulls were deep and robust, supporting musculature capable of generating strong bite forces. This adaptation facilitated efficient consumption of fibrous plants, including the dominant gymnosperms like seed ferns, cycads, and early conifers that carpeted the Triassic landscapes. Their jaws formed a sharp, parrot-like beak at the front that functioned much like modern herbivores' shearing structures, enabling them to clip vegetation cleanly. More impressively, rhynchosaurs' teeth were set in tight files on the maxilla and dentary bones, continually replacing and growing to maintain effectiveness despite constant wear. This dental battery allowed them to process plant matter with high efficiency, a critical adaptation given the tough, often nutrient-poor nature of Triassic flora. Such specialization demonstrates early herbivorous reptiles' evolutionary experiments, paralleling similar developments in later herbivorous dinosaurs such as hadrosaurs. Beyond their jaw mechanics, rhynchosaurs typically had sprawling to semi-erect limbs, enabling them to forage close to the ground for low-lying plants. Their stout, barrel-shaped bodies suggest adaptations for a lifestyle involving considerable energy expenditure in foraging and digesting high-fiber vegetation. Some fossil evidence hints at substantial population densities, indicating they were a major component of Triassic herbivore guilds. Ecologically, rhynchosaurs played a vital role as primary consumers, linking the vegetative foundations of Triassic ecosystems to carnivorous predators. Their presence supported not only their predators, such as large predatory archosaurs and rhynchosaurs, but also contributed to seed dispersal and vegetation dynamics. Like modern herbivores, their grazing likely influenced plant community composition, plant height, and even the evolution of defensive traits in plants. While rhynchosaurs were flagship herbivores, they shared their niches with diverse other early herbivorous reptiles. Among these were dicynodonts, a group of mammal-like reptiles that, though severely affected by the Permian extinction, lingered into the Triassic before eventually disappearing. Dicynodonts were characterized by their beaked mouths and tusks and filled roles as bulk plant feeders in some regions, although they became increasingly rare as the Triassic progressed. Another significant herbivore group was the aetosaurs, armored archosaurs mentioned earlier as important contributors to Triassic trophic webs. These quadrupeds sported heavy bony armor plates covering their back and flanks, and had narrow, upturned snouts suited for root and tuber digging or grazing. Their robustness suggests adaptation to browse on a wide variety of vegetation in possibly rough or open terrain environments. Furthermore, early sauropodomorph dinosaurs, often called prosauropods, emerged in the middle to late Triassic. These early relatives of the giant Jurassic sauropods were generally bipedal to facultative quadrupeds and represented a movement toward more efficient herbivory, with larger body sizes and extended necks that allowed access to higher vegetation layers. Although these forms were just beginning their evolutionary radiation in the Triassic, their eventual dominance in later periods owes much to the groundwork set down by earlier herbivores, like rhynchosaurs. Anatomically and ecologically, these herbivores exhibited a range of adaptations. From specialized dentition and jaw mechanics optimized for fibrous plant material, to limb structures supporting diverse locomotory and foraging strategies. This variety indicates partitioning of ecological niches among herbivores, reducing direct competition and enabling coexistence, an important feature of dynamic, stable ecosystems. Environmental factors during the Triassic also influenced these evolutionary pathways. Fluctuating climates, varying moisture levels, and the spread of different vegetation types created a patchwork of habitats. Herbivores adapted to these conditions in turn shaped terrestrial landscapes, for example, through selective browsing and trampling, which affected soil composition and secondary succession. Fossil sites scattered across Pangaea provide rich data illuminating rhynchosaur diversity and distribution, with especially well-studied assemblages from the Ischigualasto and Los Colorados formations in Argentina, and the Magnesian conglomerate and Chinle formations in North America. Such widespread presence underscores their ecological importance during the Triassic and illustrates evolutionary success across different continents and environments. In sum, the rise of rhynchosaurs and other early herbivores signals a pivotal shift in terrestrial ecosystems, from recovery to diversification and complexity. These groups filled essential trophic roles, facilitating energy flow from autotrophs to higher consumers, influencing the evolution of vegetation and reciprocal interactions with predators. Their evolutionary innovations, from durable dental batteries to specialized locomotion, reflect nature's responses to the challenges and opportunities presented by a radically changing world. As we proceed, we will investigate the intriguing world of prolacertiforms, aetosaurs, and other Triassic reptiles that formed an ecological web of life, paving the path for further competition, niche specialization, and ultimately, the rise of dinosaurs themselves. This many-branched tree of life during the Triassic was not merely a phase of survival, but a dynamic arena of evolutionary experimentation. As the Triassic period advanced, the evolutionary tapestry of life was woven ever more intricately, with a remarkable cast of creatures playing crucial roles in the restructuring of terrestrial ecosystems. Amid the archosaurs and early herbivores like rhynchosaurs, groups such as the prolacertiforms and aetosaurs emerged as key participants in the complex web of Triassic life. Together, these animals exemplify the rich diversity and ecological experimentation that characterized this era, illustrating how distinct clades interacted, competed, and coexisted while shaping the dynamics of their environments. The prolacertiforms were a group of elongated, primarily carnivorous reptiles that thrived during the early to middle Triassic. Although the taxonomy of this group has undergone considerable revision, prolacertiforms are often recognized by their long necks and slender bodies, which likely functioned as adaptations to a predatory lifestyle. These reptiles occupied a wide range of terrestrial and semi-aquatic habitats and were part of the broader archosauromorph radiation, a lineage that includes not just classic archosaurs, but also more basal relatives. With their elongated necks, prolacertiforms were likely agile hunters, enabling them to strike at prey from a distance or explore crevices and dense vegetation. Fossil representatives such as Prolacerta and Tanistropheus showcase this adaptation. Especially notable is Tanistropheus, which bore an astonishingly long neck, possibly longer than its body and tail combined. This unique morphology has been interpreted as an evolutionary experiment, potentially for catching fish or probing into narrow spaces to capture invertebrates and small vertebrates. The presence of prolacertiforms in diverse fossil assemblages speaks to their success and adaptability. Their specialization contrasted with the more robust, heavily armored aetosaurs, highlighting the broad ecological differentiation among reptiles of the Triassic. Aetosaurs, on the other hand, were heavily armored quadrupedal herbivores belonging to the archosaur lineage. Most abundant during the middle to late Triassic, aetosaurs were characterized by distinctive osteoderms, bony plates embedded in their skin, which formed a protective armor covering their head, back, and tail. This armor not only served as defense against predators, but also might have played a role in thermoregulation and species recognition. Aside from their armor, aetosaurs had relatively short snouts and powerful forelimbs. Their beak-shaped mouths and small leaf-shaped teeth suggest they fed primarily on low-lying vegetation, such as roots, ferns, and other plants flourishing in the shifting Triassic landscapes. Some species might have even dug into the soil to unearth tubers and roots, employing a form of ecological niche similar to that of some modern armadillos or anteaters. The ecological role of aetosaurs was significant. As sizable herbivores, they contributed to the maintenance of plant communities and served as important prey for large predator archosaurs, including Rhynchosaurs. Their armored bodies signified an evolutionary response to predation pressure, demonstrating the escalating arms race between herbivores and carnivores during the Triassic, well before dinosaurs became apex predators. Beyond the direct predator-prey dynamics, aetosaurs and prolacertiforms were part of an increasingly interconnected ecosystem where multiple trophic levels interacted. Their coexistence illustrates the complexity of niche partitioning that allowed diverse reptile groups to thrive simultaneously without direct competition, exhausting resources. This partitioning was a key factor facilitating the explosive radiation of archosauriforms and other reptiles throughout the Mesozoic. Moreover, the evolution of more elaborate food webs during the Triassic was influenced by the recovery of flora, including the expansion of seed plants like conifers and ferns. These plants provided the nutritional foundation sustaining abundant herbivores such as aetosaurs and rhynchosaurs. In turn, emerging carnivorous reptiles evolved traits to exploit these herbivorous populations, fueling coevolutionary dynamics. Intriguingly, both prolacertiforms and aetosaurs demonstrate how diverse body plans emerged as evolutionary experiments were played out in the Triassic. While prolacertiforms embraced elongation and nimbleness, Aetosaurs invested in armor and power. These distinct strategies reflect broader adaptive landscapes where survival depended on differing solutions to environmental challenges. Fossil discoveries from multiple regions, including the Americas, Europe, and parts of Asia, highlight the widespread distribution and ecological importance of these groups. Their remains help paleontologists reconstruct not only physical characteristics, but also behavioral and ecological patterns, drawing an ever clearer picture of how Triassic life flourished amid recovery. Beyond their biological significance, studying prolacertiforms and aetosaurs enriches our understanding of evolutionary mechanisms in the face of environmental stress. These clades embody resilience and innovation, traits vital for survival during eras marked by climatic fluctuations and habitat transformations. As this web of Triassic life became more intricate, interactions among species intensified, with competition and cooperation steering evolutionary trajectories. This dynamic interplay set the contextual stage for the eventual emergence of dinosaurs, who inherited ecosystems brimming with complexity and opportunity. Continuing forward, we will explore the proliferation of early reptilian forms, dissecting how competitive forces and niche specialization further sculpted the unfolding drama of the Triassic, guiding the rise toward dominance of the iconic dinosaur lineage that would ultimately captivate our imaginations through the ages. In the wake of the Great Dying, as the Triassic period unfurled its complex landscapes and challenging climates, early reptilian life experienced a remarkable proliferation that would shape the biosphere in profound ways. This era was characterized by a dynamic crucible of competition and niche formation, where evolutionary innovation met environmental opportunity, leading to the emergence of an astounding diversity of reptilian forms. Understanding this proliferation offers deep insights into how ecosystems rebuilt themselves, how species adapted to survive, and how intricate webs of life began to emerge in a world still healing from near devastation. The Triassic marked a significant evolutionary turning point. Reptiles, having endured the mass extinction, seized the emptied ecological canvases with unprecedented vigor. This diversification was not a random flourish, but a carefully fashioned response to selective pressures, ranging from climate variability and resource availability to interspecific competition and predator-prey dynamics. Such pressures fostered the differentiation of species, allowing them to occupy increasingly specialized ecological niches and reduce direct competition, thereby promoting ecosystem stability. At the foundation of this evolutionary expansion lay archosauriform reptiles, including early relatives of both crocodilians and dinosaurs, as well as various enigmatic groups. These taxa began to fill diverse roles: apex predators, opportunistic carnivores, herbivores, insectivores, and more. Concurrently, other reptilian lineages, such as lepidosauromorphs, ancestors to modern lizards and snakes, proliferated, although their early Triassic history is less abundant in the fossil record. Competition was a defining force driving this proliferation. As diverse reptilian species scrambled to exploit evolving habitats, natural selection favored traits that conferred advantages in resource acquisition, mobility, reproduction, and defense. For instance, locomotor innovation was paramount. Some reptiles maintained sprawling postures, well adapted for ambush or aquatic environments. Others developed semi-erect to fully erect limb postures, enabling sustained activity and greater energetic efficiency. This variation facilitated the occupation of broad habitat spectra, from dense forests to open floodplains and riverine systems. Dietary specialization further partitioned the niche space. Early reptiles displayed an array of feeding adaptations, from herbivory grinding teeth in rhynchosaurs and aetosaurs to sharp slicing dentition in predatory archosaurs and prolacertiforms. Such differentiation was crucial in minimizing niche overlap among coexisting species, allowing herbivores to focus on specific plant types or parts, while carnivores specialized in particular prey sizes or hunting strategies. An often overlooked but vital aspect of this diversification was reproductive strategy. While all reptiles of this era remained oviparous, variations in nesting behavior, egg size, and clutch characteristics may have influenced survival rates and population dynamics. Some species might have adopted semi-social behaviors linked to nesting sites, though clear evidence remains scarce due to fossilization biases. Habitat heterogeneity fostered ecological distinctiveness as well. The unification of Earth's land masses into the supercontinent Pangaea created expansive, dry continental interiors punctuated by wetter coastal and riverine corridors. Deserts, floodplains, and lush, fern-filled wetlands coexisted within relatively constrained geographic bounds. Reptilian species exhibited remarkable ecological plasticity in adapting to these varying conditions, with some favoring arid, adapted, water-conserving physiologies, whereas others flourished in more mesic environments. Interpopulation interactions became increasingly complex. Competition for food and territory led to spatial segregation among species. Social behaviors, while not fully understood, likely played roles in territory defense, mating, and group foraging. Furthermore, predator-prey dynamics exerted reciprocal selective pressures, fostering adaptations such as enhanced sensory organs, camouflage, speed, or defense mechanisms like armor plating. Of particular interest are the evolutionary arms races that escalated during this time. Herbivores developed tougher dental batteries or bony armor to resist increasingly efficient carnivore attack strategies. In turn, predators evolved sharper teeth, stronger jaws, and greater locomotor capabilities to overcome prey defenses. This feedback loop of adaptations propelled diversification and specialization across taxa. The fossil record, though incomplete, paints a picture of explosive reptilian radiations. Sites across Pangaea reveal assemblages comprising early dinosauriforms, rhynchosaurs, rhynchosaurs, aetosaurs, prolacertiforms, and smaller reptiles sharing habitats. Their coexistence within overlapping temporal and geographical ranges evidences that early reptiles did not simply replace one another, but rather co-evolved through intricate interactions, contributing to ecosystem resilience. Molecular and anatomical data support the notion that this era set the stage for the eventual dominance of dinosaurs. Specific morphological innovations, such as changes in hip structure, limb alignment, and respiratory systems, were refined in this competitive environment. These innovations enhanced metabolic efficiency, locomotion, and predator-prey capabilities, giving rise to lineages with superior adaptive potential. The proliferation of early reptilian life also interfaced with changes in flora and climate. Shifts in plant communities, including the spread of gymnosperms, provided new food resources that shaped herbivore diet evolution. Climatic fluctuations, periodic shifts between aridity and humidity, imposed environmental filters, selecting for species able to endure variability and colonize novel niches. In examining this period, it becomes clear that the triadic forces of competition, niche formation, and adaptation fostered a dynamic evolutionary arena. Species not only survived but strategically diversified, exploiting ecological opportunities with increasing precision and sophistication. This intricate interplay forged vibrant, structured ecosystems characterized by specialization and interdependence. Overall, the Triassic proliferation of reptiles was a critical epoch of innovation, underpinning the future evolutionary trajectories of vertebrate life. The patterns of competition and niche partitioning witnessed during this time remind us that biodiversity arises through relentless interaction, not merely survival, but the continuous balancing of conflict and cooperation within the living world. As we move forward in this exploration, we will delve into the emergence of the very first dinosaurs themselves, tracing their origins amidst these competitive landscapes and shining light on how they began to distinguish themselves anatomically, behaviorally, and ecologically from their precursors and contemporaries. This story of origin will deepen our understanding of how ancient rivals contended, and ultimately how dinosaurs began their inexorable climb toward dominance. Emerging from the tumultuous backdrop of the late Triassic, the first true dinosaurs trace their origin to a time of sweeping ecological changes and intense evolutionary pressures. These ancient reptiles, though modest in size and diversity at their inception, would ignite an evolutionary revolution that ultimately saw them monopolize terrestrial ecosystems for millions of years. To understand the rise of dinosaurs, it is essential to explore their ancestral roots, the environmental conditions that shaped their early evolution, and how their closest relatives coexisted and competed within Triassic landscapes. Dinosaurs belong to a clade called Dinosauria, a group within the larger Archosauria, which also includes pterosaurs and crocodile-line reptiles. The earliest dinosaurs appeared sometime in the middle to late Triassic, around 230 million years ago, during a period when Earth was recovering from previous mass extinctions and its ecosystems were undergoing rapid restructuring. These nascent dinosaurs were initially small, bipedal, and comparatively lightly built, a stark contrast to the immense beasts they would become in later periods. Among the earliest dinosaur genera known from the fossil record are Herrerasaurus and Eoraptor, both found in the Ischigualasto Formation of Argentina, a renowned Triassic site that has yielded invaluable insights into early dinosaur evolution. Herrerasaurus, a carnivorous theropod, was approximately 6 meters long, predatory, and likely a swift, skilled hunter. Eoraptor, smaller and more primitive, displayed a blend of basal features and early specialized traits, possibly indicating a more omnivorous or opportunistic diet. Tracing the evolutionary origins of these dinosaurs leads us further back, to their close relatives often lumped under a paraphyletic group sometimes called dinosauriforms. These dinosauriforms, including genera like Marasuchus and Lagerpeton from South America, possessed many dinosaur-like characteristics but lacked some defining features that would later unify Dinosauria. Anatomically, dinosauriforms exhibited erect limb postures, elongated metatarsals, foot bones, suited for agile movement, and changes in pelvic structure that presaged the iconic dinosaurian hip. These innovations granted them enhanced locomotor efficiency and the ability to sustain more active lifestyles than more primitive reptiles. Their success in diverse Triassic environments made them the evolutionary crucible for the eventual emergence of dinosaurs. The evolutionary transitions leading to true dinosaurs involved gradual acquisition of multiple anatomical traits. These included developments such as a perforated acetabulum, a hole in the hip socket, which lightened the pelvis and allowed for stronger muscle attachment, facilitating powerful bipedal locomotion. Skull modifications also occurred, including changes in jaw muscle arrangement that enabled more efficient biting. Additionally, the wrist bones of theropod ancestors underwent transformations, facilitating grasping and manipulation, features significant for predatory behaviors. Climatic and ecological factors of the late Triassic played critical roles in shaping these evolutionary trajectories. Increasing aridity in many regions of Pangaea and the mosaic nature of habitats created spatially heterogeneous selective pressures. Such conditions favored animals capable of exploiting diverse niches and possessing metabolic and locomotor capabilities adaptable to variable environments. Competition with other archosaurs, such as the crocodile line crurotarsans, and herbivorous reptiles sharing similar niches, was fierce. Dinosaurs coexisted with rhynchosaurs, aetosaurs, rhynchosaurs, and prolacertiforms. Their initial small sizes and agile postures could have conferred advantages in evading larger predators and exploiting underutilized ecological niches, such as swift predation of smaller prey and active foraging. Fossil evidence also suggests early dinosaurs diversified into two principal lineages: the ornithischians, characterized by a distinctive pelvis structure often compared to that of birds, and the saurischιans, which include the ancestors of both the large sauropodomorph herbivores and the carnivorous theropods. This divergence set up evolutionary pathways that would lead to monumental diversity in diet, morphology, and behavior. Paleontological discoveries continue to refine our understanding of dinosaur origins. For example, new fossils indicate that some early dinosaurs may have had proto-feathers or simple filamentous integuments, hinting at thermoregulatory adaptations and perhaps social signaling, features once thought to be exclusive to later theropods and birds. These findings emphasize the evolutionary experimentation occurring well before the Jurassic explosion of dinosaurs. Moreover, the global distribution of early dinosaur fossils reveals that they spread relatively rapidly across Pangaea, finding footholds in varying climates and habitats. This widespread presence testifies to their ecological flexibility and resilience during a time of ongoing environmental fluctuations. In essence, the rise of the first dinosaurs was less an abrupt takeover and more a gradual process of emergence through a crucible of competition, adaptation, and opportunity. Their ancestors set evolutionary foundations in locomotion, metabolism, and feeding strategies. And from these preconditions, dinosaurs developed distinctive traits that would eventually dominate terrestrial ecosystems. As we explore the anatomical innovations and survival strategies that defined these early dinosaurs, it becomes clear how their evolutionary legacy is a story of persistence and gradual mastery over an ever-changing world. This understanding forms the cornerstone for comprehending the spectacular diversification that would follow in the Mesozoic, unlocking the rich and complex saga of dinosaurian dominance on Earth. Among the many mysteries and marvels of the Triassic era, one of the most fascinating narratives is the anatomical and functional innovations that early dinosaurs developed. Innovations that distinguished them from their contemporaries and provided them with unique tools for survival and eventual dominance. Exploring the fundamental aspects of dinosaur anatomy reveals not only the story of evolutionary design, but also the biological ingenuity that supported these reptiles' success in an often harsh and competitive world. At the heart of dinosaur innovation lies their skeletal structure, carefully weighted and fashioned for both strength and efficiency. Unlike many earlier reptiles which retained sprawling postures, dinosaurs featured an erect limb orientation, with legs positioned directly beneath the body. This biomechanical arrangement allowed for more efficient support of body weight and facilitated greater mobility and endurance. By elevating the limbs, dinosaurs reduced the energy costs of locomotion, enabling them to move swiftly across diverse terrains. This design also opened pathways for various locomotive modes, including bipedalism and quadrupedalism, which would be refined in later dinosaur lineages. The pelvis is another hallmark of dinosaur anatomy, divided principally into two groups: Saurischia, lizard-hipped, and Ornithischia, bird-hipped. The anatomy of the hip provides clues to their evolutionary pathways and functional capabilities. Saurischιans retained a more primitive pubis-oriented forward pelvis orientation, supporting large muscular legs advantageous for powerful strides and predation or large-scale herbivory. Ornithischians, meanwhile, developed a backward-pointing pubis that allowed for better balance and potentially a larger gut cavity to digest fibrous plant material. This pelvic diversity illustrates how structural modifications were aligned with lifestyles and dietary adaptations. Dinosaur skulls showcase an array of evolutionary experimentation. Early theropods, such as Herrerasaurus, possessed large, elongated skulls with sharp, serrated teeth designed for slicing flesh efficiently, typifying carnivorous adaptations. In contrast, early ornithischians developed beak-like structures adept at cropping vegetation, accompanied by complex dental batteries with closely packed teeth designed to grind plant matter, an advancement crucial for processing fibrous foliage. These dental adaptations highlight the advance from more generalized to specialized feeding strategies. The vertebral column in dinosaurs also presents remarkable features, combining robustness with flexibility. Many species developed reinforced vertebrae with air sacs, an innovation inherited through their archosaur ancestors, which lightened the skeleton and enhanced respiratory efficiency. This pneumaticity allowed large-bodied dinosaurs to evolve without the prohibitive weight typically constricting terrestrial animals of massive size. Forelimbs and hind limbs reflect additional diversification. Theropods increasingly exhibited grasping hands with flexible wrists, allowing manipulation of prey or environmental objects, a pre-adaptation evident in birds' later evolution. Conversely, sauropodomorphs, the long-necked herbivorous dinosaurs, evolved massive, pillar-like limbs to support enormous body masses and enabled slow but sustained foraging. Digit morphology, claw shape, and limb proportions continued to evolve in correspondence with feeding ecology and locomotion. One of the greatest innovations was the respiratory system. Dinosaurs, like modern birds, are believed to have possessed a unidirectional airflow system in their lungs, vastly improving oxygen extraction and endurance. This adaptation was especially advantageous under the often fluctuating oxygen levels and hot climates of the Triassic and later periods, contributing to greater metabolic efficiency and activity levels. Sensory systems were also highly developed. Fossil evidence points to advanced visual capabilities, with many theropods showing forward-facing eyes and stereoscopic vision for accurate depth perception, essential for hunting and environmental awareness. Olfactory bulbs, responsible for the sense of smell, were well developed in many forms, augmenting their ability to detect prey, predators, or mates. Skin and integumentary structures have increasingly come under scientific scrutiny for their importance in dinosaur biology. While the image of scaly skin dominates popular imagination, many early dinosaurs likely sported primitive feathers or filamentous coverings. These protofeathers possibly played roles in thermoregulation, display, and species recognition well before the emergence of flight in birds. Such integumentary innovations reflect the complexity of dinosaur physiology beyond bones and teeth. Reproductive adaptations further facilitated dinosaur success. The evolution of eggs with calcareous hardened shells provided environmental protection for embryos, crucial in the diverse and variable terrestrial habitats dinosaurs occupied. Nesting behaviors and potential parental care, inferred from fossilized nesting sites and embryonic remains, suggest social and reproductive strategies that increased offspring survival. Understanding dinosaur anatomy also invites reflection on their metabolic strategies. Although debate persists on the exact nature of dinosaur metabolism, a broad consensus supports that many dinosaurs possessed at least a mesothermic physiology, a metabolic state between ectothermy, cold-bloodedness, and endothermy, warm-bloodedness. This metabolic flexibility likely contributed to their ability to occupy diverse ecological niches and endure variable climates. In sum, the anatomical and functional innovations of early dinosaurs represent a suite of integrated evolutionary solutions to challenges posed by their environment. From limb posture and digestive adaptations to respiratory efficiency and sensory acuity, these traits collectively crafted animals that were not just survivors, but versatile and dynamic agents of change within their ecosystems. As we proceed, these anatomical foundations will inform deeper discussions about the competitive interactions dinosaurs faced, their behavioral ecology, and how incremental innovations translated into the eventual unparalleled dominance witnessed in subsequent geological periods. The anatomy of dinosaurs is not merely a reflection of form, but a testament to the evolutionary interplay between life and environment, a story etched in bone as well as in the very earth itself. In the vast and volatile landscapes of the Triassic period, the story of survival was not merely a tale of singular ascendancy, but a complex narrative weaving together competition, adaptation, and ecological interplay among diverse reptilian lineages. Among the most significant of these rivalries was that between the early dinosaurs and their formidable contemporaries, the crurotarsans, those crocodile-line archosaurs who had established themselves as dominant predators and ecological players long before dinosaurs fully rose to prominence. This section delves deep into the competitive dynamics between these two groups, revealing how their interactions shaped the evolutionary outcomes that molded Mesozoic ecosystems. Crurotarsans, sometimes referred to as pseudosuchians, are a paraphyletic assemblage characterized by their distinctive ankle morphology, featuring a specialized, flexible joint called the crurotarsal ankle. This adaptation provided many members of this group with remarkable maneuverability and power, facilitating a sprawling to semi-erect gait that suited their varied lifestyles. Among these crocodile-line archosaurs were rhynchosaurs, phytosaurs, aetosaurs, and other less well-known lineages. In the early and middle Triassic, crurotarsans dominated much of the terrestrial apex predator niches. Rhynchosaurs, for example, were large, robust predators with powerful jaws and sharp, serrated teeth designed to dispatch sizable prey. Their heavily muscled limbs and often sprawling stance made them well adapted for ambush predation or bouts of sudden, forceful attack, specializing in overpowering rather than sustained chases. Phytosaurs, resembling modern crocodilians in body plan, occupied semi-aquatic niches and dominated waterway predation. Aetosaurs, armored herbivores, occupied primary consumer niches effectively, their heavy armor providing defense against predators within this intricate food web. Dinosaurs, emerging initially as relatively small, bipedal forms, faced stiff competition from these ecologically entrenched crurotarsans. Early dinosaurs, such as herrerasaurids and early sauropodomorphs, coexisted with crurotarsans across Pangaea, often competing for similar prey or habitats. The smaller size and erect posture of dinosaurs enabled them to exploit different hunting strategies, including greater endurance and agility, favoring active pursuit or cursorial predation. The dynamics between these groups were shaped by multiple factors: anatomical, ecological, and environmental. Crurotarsans, with their often larger body sizes and sprawl-adapted limbs, excelled in power and ambush tactics, thriving in habitats that favored concealment and sudden attacks. Dinosaurs' erect limbs and more gracile form favored sustained locomotion and endurance, granting advantages in open or more variable terrains. Predatory niche partitioning likely reduced direct competition in many cases. While Rhynchosaurs might have targeted large herbivores or exerted dominion over specific territories, early theropod dinosaurs focused on smaller prey or different hunting strategies. This differentiation enabled coexistence, but also fueled an evolutionary arms race where each group refined adaptations to outcompete the other. Environmental changes during the late Triassic, including shifts in climate and habitat fragmentation, appear to have gradually favored the dinosaurian mode of life. Increasing aridity and the expansion of open landscapes likely advantaged creatures capable of efficient, endurance-based locomotion, traits more characteristic of dinosaurs. Conversely, the large, sprawling crurotarsans were more restricted in ecological flexibility, potentially contributing to their decline. Fossil evidence affirms this competitive interplay. Stratigraphic layers reveal declines in crurotarsan diversity temporally coincident with the rise and radiative expansion of dinosaurs. The final phases of the Triassic witnessed the disappearance of many Rauisuchians and phytosaurs, paralleled by the increasing dominance of Saurischian and Ornithischian dinosaurs across various regions. It is important to note, however, that this shift was not instantaneous or predestined. The late Triassic extinction events, such as those triggered by volcanic activity and climate upheavals, played significant roles in reshaping ecosystems. Dinosaurs, perhaps owing to their anatomical and physiological traits, were better equipped to survive these crises and capitalize on vacated niches previously held by crurotarsans. The nuanced tale of competition between dinosaurs and crurotarsans underscores the multifaceted nature of evolutionary success. It was a combination of functional morphology, reproductive strategies, metabolic adaptations, and ecological opportunism that tipped the scales in favor of dinosaurs over their crocodilian predecessors. Their advantage in locomotion and metabolic efficiency, coupled with flexible diets and reproductive modes, allowed dinosaurs to explore new lifestyles and environments effectively. Furthermore, the carnivorous dinosaurs' development of bipedalism, a subject to be explored in detail later, enhanced their mobility and hunting efficiency, which likely facilitated their ascendancy in predatory roles once dominated by crurotarsans. In conclusion, the early rivalry between dinosaurs and crurotarsans represents a vital chapter in the evolutionary saga of terrestrial vertebrates. It was a contest of form, function, and adaptability played out across millions of years in a world rife with challenges and opportunities. Understanding this competition not only illuminates the forces behind dinosaur dominance, but also enriches our grasp of how life continually evolves through contest and collaboration. As conditions shifted and new ecological landscapes emerged, the dinosaur lineage gradually solidified its foothold, heralding an era that would see these remarkable creatures transform Earth's biota forever. Moving forward, we will explore one of the key anatomical transformations tied to this rise, the advent of bipedalism, and examine how this pivotal evolutionary innovation conferred unprecedented advantages to dinosaurs as they negotiated the challenges of survival and competition in the Triassic. In the intricate saga of dinosaur evolution, few adaptations are as transformative and emblematic as bipedalism, the ability to walk and run on two legs. This anatomical innovation emerged early in dinosaur history and conferred a suite of remarkable advantages that not only enhanced survival in the competitive Triassic ecosystems, but also paved the way for the enormous evolutionary diversity and success of dinosaurs throughout the Mesozoic. Understanding the development and implications of bipedalism reveals much about how early dinosaurs navigated challenges and opportunities in a world shared with robust competitors like the crurotarsans. Bipedalism in dinosaurs is not a mere quirk of locomotion. It represents a profound reorganization of the skeletal, muscular, and nervous systems. Early dinosaurs and their close relatives transitioned from the ancestral sprawling or semi-erect postures common among terrestrial reptiles to an upright stance in which the hind limbs bore the full weight of the body. This limb configuration facilitated efficient propulsion, balance, and agility, allowing better exploitation of the environment and enhancing hunting and evasion capabilities. From a biomechanical standpoint, walking on two legs confers significant energy benefits. With the body's center of gravity positioned over the hips, bipedal animals can have longer, more powerful strides, reducing fatigue during sustained locomotion. This endurance capability was crucial for early theropods, carnivorous dinosaurs that relied on chasing down agile prey or patrolling large territories for resources. It is plausible that bipedalism enhanced their ability to cover vast distances, marry speed with stamina, and allocate forelimbs for specialized functions like grasping, manipulating, or slashing. Forelimb freedom is among the most consequential effects of bipedalism. Early bipedal dinosaurs could evolve forelimbs with enhanced dexterity and varying lengths, enabling complex behaviors such as capturing prey, nesting, or even primitive display behaviors to communicate with conspecifics. This manipulation capacity may have led to selective pressures that encouraged cognitive development and increased brain complexity, aligning with the concept that anatomical innovation can foster new behavioral and evolutionary potentials. Bipedalism also influenced feeding ecology. By positioning the head and upper body higher, dinosaurs gained access to different food sources. Herbivorous forms could reach higher vegetation, while carnivorous species benefited from enhanced visual perspectives to spot prey or rivals over vegetated or rugged terrain. This vertical positioning expanded ecological niches and reduced direct competition for resources among species employing different strategies and locomotor behaviors. The skeletal adaptations underpinning bipedalism included robust pelvic girdles that could sustain the body's weight, elongated femurs for increased stride length, and modifications in foot structure, such as 3 weight-bearing toes that afforded greater stability and traction. Muscular arrangements evolved to support swift acceleration and agile maneuvering. The tail, often long and stiffened by bony structures called ossified tendons, served as a counterbalance, refining balance during rapid movement and turns. These physical traits are well documented in fossil specimens of early bipedal dinosaurs like Herrerasaurus, Eoraptor, and Coelophysis. These animals showcase the blend of lightweight build, limb proportions, and skeletal reinforcements that typify bipedal locomotion, underscoring how the anatomy reflected functional innovations. Interestingly, the subtle variations in limb length and body center among these species hint at diverse locomotor behaviors and ecological roles, affirming that bipedalism was not a single uniform adaptation, but one subject to evolutionary fine-tuning. Importantly, bipedalism should be viewed within the broader context of the Triassic environment, where complex ecosystems featured diverse predators and herbivores, shifting climatic patterns, and variable topographies. The efficiency and flexibility imparted by bipedal gait would have provided early dinosaurs with strategic advantages, especially in escaping or pursuing prey, navigating heterogeneous terrains, and surviving environmental stresses. Moreover, bipedalism may have indirectly influenced social behaviors by freeing forelimbs for gestures or tactile communication during mating or territorial interactions, a hypothesis supported by the later emergence of evidence for complex sociality in dinosaurs. As such, the functional benefits of bipedalism transcended locomotion, intersecting with behavioral and reproductive strategies that enriched dinosaur evolutionary success. From an evolutionary perspective, bipedalism represents a trade-off. While it confers increased agility and forelimb utility, it also demands sophisticated neuromuscular control and balance. The evolutionary conservation and elaboration of bipedalism in dinosaur lineages reflect how these challenges were met through natural selection, favoring genetic and developmental mechanisms that stabilized this locomotor mode. In summary, the advent of bipedalism in early dinosaurs marked a pivotal evolutionary milestone. It redefined the ways these creatures interacted with their environment and competitors by enhancing mobility, feeding opportunities, and behavioral potential. By examining the anatomical modifications and ecological context of bipedalism, we gain a clearer view of how this trait acted as a cornerstone for the rise of dinosaurs from modest beginnings to apex roles. As we continue to explore the rich ecology of the Triassic, attention will turn toward how environmental pressures, often chaotic and extreme, served as powerful selective forces molding dinosaur evolution. The benefits of bipedalism would be tested and refined through fluctuating climates, resource challenges, and fierce competition, all of which helped shape the remarkable adaptability that became a hallmark of dinosaur success. The Triassic period, a bridge between the ravages of the Permian mass extinction and the flourishing of the Jurassic era, was marked by dramatic climate fluctuations and environmental extremes. These chaotic conditions acted as powerful selective pressures, profoundly influencing the evolutionary pathways of the early reptiles, including the first dinosaurs. To appreciate the rise of these ancient creatures, one must first understand the turbulent climatic backdrop against which their stories unfolded, a world of shifting temperatures, repeated aridity and humidity cycles, and volatile atmospheric conditions. The formation of the vast supercontinent Pangaea during the Triassic deeply shaped global climates. With almost all land masses fused into one, the planet experienced extreme continental climates, characterized by intense seasonal variations, widespread aridity in continental interiors, and stormy monsoonal systems along coasts. Unlike today's relatively more stable climate belts, Triassic regions often swung between prolonged droughts and episodic heavy rainfall. This patchwork of moisture extremes generated a heterogeneous mosaic of habitats: arid deserts dotted with ephemeral lakes, riverine floodplains swelled irregularly by monsoonal deluges, and coastal margins moderated by oceanic influence. Moreover, volcanic activity, particularly the voluminous eruptions associated with the Central Atlantic Magmatic Province, CAMP, toward the late Triassic, had substantial climatic impacts. These massive volcanic events released vast quantities of greenhouse gases, carbon dioxide, sulfur dioxide, and methane, into the atmosphere. The elevated greenhouse gas concentrations led to global warming, acid rain, and disruptions of the carbon cycle. Such environmental stresses contributed to early episodes of extinction and ecological turnover, altering habitats and resource availability. These climatic perturbations translated into oscillating selection pressures favoring organisms with adaptability and resilience over specialization. For early dinosaurs and their contemporaries, survival depended on coping with severe water scarcity during dry spells and exploiting abundant but transient resources during wet intervals. Physiological adaptations such as efficient water retention, metabolic regulation, and behavioral strategies became critical for enduring environmental unpredictability. The fluctuating weather patterns also influenced vegetation dynamics. Plant communities had to navigate cycles of desiccation and proliferation, leading to shifts in dominant flora over relatively short geological periods. Such changes directly impacted herbivorous reptiles, which in turn shaped the trophic landscapes. The expansion of drought-tolerant gymnosperms, like conifers in arid regions, contrasted with the flourishing of ferns and seed ferns in wetter zones. Herbivores capable of dietary flexibility or migration had evolutionary advantages in such spatially and temporally variable conditions. From an evolutionary perspective, these environmental extremes propelled experimentation. Species exhibiting plasticity in growth rates, reproductive timing, and foraging behavior could better track shifting resources. The ability to disperse across geographically fragmented habitats helped some lineages avoid localized extinctions when droughts or floods transformed ecosystems. Evidence from fossil isotope analyses indicates that some early dinosaurs maintained relatively high metabolic rates, a factor that may have facilitated sustained activity despite thermal stresses. Furthermore, climate chaos intensified interspecific competition. Limited water resources and fluctuating food supplies heightened rivalry among reptiles, amphibians, and other vertebrates for survival. This pressure likely accelerated the evolution of novel locomotor adaptations, efficient hunting strategies, and social behaviors promoting resource partitioning. Predators evolved sharper senses and faster reflexes to exploit scarce prey, while herbivores developed tougher dentition and gut systems for exploiting scarce or poor-quality forage. Another layer of complexity stems from the interplay between climate shifts and episodic mass extinction events within the Triassic, such as the Carnian pluvial episode. A relatively brief but significant interval, marked by increased rainfall, ecological turnover, and diversification of dinosaurs and other groups. These intervals of climatic upheaval acted as filters, selectively pruning vulnerable species while allowing adaptable ones to diversify rapidly. Sedimentary records across former Triassic basins reveal the physical imprint of these chaotic climates. Alternating deposits of red beds signifying arid conditions, interspersed with layers indicative of flooding and lake formation. Such geological insights corroborate the existence of high-amplitude environmental swings continually reshaping ecosystems. In this context, the evolutionary narrative of Triassic life emerges as a testament to adaptability in the face of persistent turmoil. The physiological, anatomical, and behavioral innovations enabling early dinosaurs and their contemporaries to thrive reflect a balance between resilience and opportunism. Their success was not merely a triumph of brute strength or size, but of versatility, a biological nimbleness finely tuned to environmental unpredictability. In summary, climate chaos during the Triassic period was a crucible that forged the evolutionary paths of terrestrial reptiles. Environmental extremes acted as relentless selective forces, steering adaptation in ways that would define life's trajectory beyond the Triassic. In the upcoming sections, we will explore how these pressures drove resource competition, feeding strategies, and social behaviors among dinosaurs, revealing the nuanced interplay of biology and environment that underscored their path to dominance. In the complex mosaic of Triassic ecosystems, the struggle for survival often revolved around the fundamental need to acquire energy and nutrients, a challenge that ignited intense resource wars among the burgeoning fauna. Feeding strategies and dietary specializations became critical battlegrounds where evolutionary innovation, competition, and ecological interplay unfolded. These specialized adaptations not only allowed species to carve distinct niches, but also underpinned the dynamic and resilient food webs that characterized the Triassic period. Resource acquisition is the cornerstone of ecological success. After the devastating ecological reset caused by the Permian-Triassic mass extinction, the opportunity and imperative to exploit available nourishment was unprecedented for many emerging lineages. Yet the post-extinction landscapes featured highly heterogeneous flora and fauna availability, unevenly distributed across Pangaea's vast terrains. In this resource-limited, unstable framework, diversification of diets and feeding adaptations became pivotal drivers of both survival and diversification. On the vegetation front, early Triassic flora was dominated by seed plants like gymnosperms, including conifers, cycads, and seed ferns, alongside ferns and other spore-producing plants. This floristic mix presented a variety of structural complexities and chemical defenses. Herbivorous reptiles, from the rhynchosaurs with their sophisticated beaks and grinding teeth, to the armored aetosaurs with specialized mouthparts, evolved distinctive mechanical and physiological adaptations to digest these fibrous, sometimes toxic, plant materials efficiently. For instance, rhynchosaurs had robust jaw mechanics facilitated by broad, beak-like structures and tightly packed rows of continually replaced teeth that worked as grinding surfaces, ideal for processing tough vegetation. This dental battery can be seen as a precursor to later, more complex herbivore adaptations seen in Jurassic and Cretaceous dinosaurs. Similarly, aetosaurs possessed leaf-shaped teeth suited for browsing, combined with their bony armor providing defense against predators, exemplifying a unique balance of offense and defense strategies related to feeding and survival. Dietary specialization was a key evolutionary response to reduce direct competition. Differing preferences for plant parts, leaves, stems, roots, or seeds, and the ability to detoxify or avoid plant secondary metabolites allowed multiple herbivore species to coexist by partitioning resources. Variations in feeding height also contributed. Some herbivores grazed close to the ground, while others could browse taller vegetation, an early indication of vertical niche differentiation. Meanwhile, carnivorous reptiles, particularly early theropods and large crurotarsans, like rauisuchians, developed adaptations that enhanced hunting efficiency. Serrated, blade-like teeth capable of slicing meat and powerful jaw muscles were primary weapons in securing prey. Forelimbs and claws could be sharp and dexterous, aiding in grasping and subduing prey. Some predatory species likely exhibited opportunistic feeding, expanding diets to include scavenging or small prey to cope with resource unpredictability. Locomotion and sensory adaptations complemented feeding strategies. Cursorial abilities, the capacity for sustained running, favored predators that could chase agile prey or explore vast territories for food. Vision, olfaction, and even social hunting cooperation, though rare and poorly documented in Triassic reptiles, probably played roles in enhancing feeding success. In aquatic and semi-aquatic realms, feeding strategies also diversified. Phytosaurs, resembling modern crocodilians, were predominantly fish and small vertebrate feeders, using their elongated snouts packed with conical teeth to seize slippery prey. Their ambush predation style underpinned the food webs in Triassic rivers and lakes. The evolutionary interplay between predator and prey fueled reciprocal adaptations. Better defenses in herbivores, like armored plating or speed and camouflage, selected for greater predatory efficiency and vice versa. This technological arms race, encompassing teeth, claws, and even social behavior, intensified the ecological complexity of Triassic communities. These feeding strategies and specializations laid the groundwork for increasingly elaborate trophic networks. Energy flow from primary producers through herbivores to carnivores became more streamlined and robust compared to the simplified systems immediately following the Great Dying. In sum, the resource wars of the Triassic era were a crucible for biological innovation that fueled the diversification of feeding adaptations and dietary niches. This evolutionary experimentation underpinned ecological stability and complexity, setting the stage for the expansive radiation of dinosaurs and their contemporaries in subsequent periods. As we advance, the social and behavioral dimensions of these early dinosaurs, including territoriality and community dynamics, come into sharper focus, highlighting how feeding strategies intertwined with social organization to shape survival and evolutionary success. As the Triassic period progressed, the evolutionary landscape not only witnessed remarkable anatomical innovations and ecological expansions, but also the emergence of complex social behaviors among early dinosaurs and their contemporaries. The establishment of territoriality, social structures, and rudimentary communities marked a critical transition in the behavioral ecology of vertebrates, signaling new levels of interaction within and between species. Exploring these dimensions sheds light on how the first dinosaur communities negotiated survival amidst competition and environmental challenges, setting foundations for the social complexities observed in later Mesozoic ecosystems. Territoriality, the defense of a specific area against intruders, likely evolved as a strategy to secure vital resources such as food, nesting sites, and mating opportunities. Early dinosaurs, although generally smaller and less conspicuous than their later counterparts, showed anatomical and behavioral traits suggestive of territorial behavior. Fossil evidence, such as the spatial distribution of trackways and nesting sites, implies that some species maintained home ranges or territories that they vigorously defended against conspecifics or rival species. By holding territories, individuals or groups could reduce intraspecies competition, safeguard food resources, and improve reproductive success. Social behavior in these nascent communities was likely multifaceted. Some early dinosaurs probably exhibited solitary territoriality typical of many reptiles, while others may have formed loose associations or small groups. The discovery of fossil beds containing multiple individuals of the same dinosaur species, arranged in a clustered formation, supports the idea that gregariousness and even cooperative behaviors were part of their ecology. This sociality could have facilitated collective defense against predators, increased foraging efficiency, or enhanced breeding success through protection of nests and juveniles. The presence of nests and evidence of parental care in the fossil record, although rare for the Triassic, suggests that some early dinosaurs engaged in reproductive strategies beyond mere egg-laying. Parental investment in offspring, through nest guarding or provisioning, would have increased juvenile survival rates and fostered the development of social bonds. Such behaviors also hint at cognitive capacities, underpinning communication and behavioral coordination within groups. Territorial and social behaviors were influenced by environmental factors and resource distribution. In the patchy and often resource-scarce landscapes of the Triassic, competition for food and safe nesting spots was intense. Defensible territories reduced unpredictable interspecific interactions and allowed for optimized resource use. Seasonal climate variability likely reinforced territoriality as resource availability fluctuated, necessitating the defense of reliable food and water sources during harsh periods. Communication among early dinosaurs and their contemporaries probably involved a combination of visual signals, vocalizations, and perhaps olfactory cues. Features such as crests, frills, and body coloration, while better documented in later dinosaurs, likely had their behavioral roots in the Triassic. These physical traits might have played roles in species recognition, mating displays, or dominance hierarchies. Even simple postural and movement cues could have transmitted important social information, facilitating peaceful coexistence or aggressive deterrence. Comparative studies of modern reptiles and birds, the closest living relatives of dinosaurs, provide insights into possible behavioral parallels. Many modern reptiles exhibit territorial displays and social hierarchies, while certain bird species showcase complex communal breeding and cooperative care, suggesting that the evolutionary seeds of such behaviors were present early on. The formation of early dinosaur communities also indicates an evolutionary trend toward increased social complexity. These communities would have structured ecosystems both spatially and functionally. Group living afforded benefits such as enhanced protection from predators, shared vigilance, and optimized resource exploitation, fostering stability and resilience in Triassic habitats. Furthermore, social behavior influenced evolutionary trajectories beyond immediate survival. It enabled sexual selection pressures, driving the development of secondary sexual characteristics and elaborate behaviors that played roles in mating success and reproductive isolation, key components in speciation. Yet, these behaviors did not exist in a vacuum. Interactions with other vertebrates, especially contemporaneous archosaurs like crurotarsans, shaped early dinosaur social ecology. Predation pressures might have fostered tighter group cohesion or territorial expansions. Conversely, competition over nesting sites and resources could have influenced the spatial dynamics and behavioral flexibility within communities. In conclusion, territoriality and social behavior among the first dinosaurs represented critical adaptations, enabling more efficient resource use, improved defense, and reproductive success. These behaviors laid the groundwork for the complex social structures seen in later dinosaur groups and underscore the intricate balance between biology and environment during the dawn of dinosaurian evolution. As we progress, we will examine predator-prey dynamics in greater detail, exploring the life and death contests within Triassic ecosystems and how these interactions further molded the evolutionary destinies of dinosaurs and their rivals. The Triassic period, a crucible of evolutionary reinvention, was characterized by complex and often brutal predator-prey dynamics that shaped the biological theater of life and death across Pangaea's emerging ecosystems. These interactions were not mere contests of brute strength, but intricate relationships reflecting a profound evolutionary arms race where strategies of survival, evasion, and predation recursively influenced anatomy, behavior, and ecology. To truly understand the rise of dinosaurs and their eventual dominance, it's essential to delve into the nuanced predator-prey dances that choreographed life in the Triassic. At the dawn of the Triassic, the catastrophic Great Dying had left ecosystems disrupted and simplified, with numerous predator niches emptied by mass extinction. This void enabled new predators, among them archosaurs, including early crurotarsans and the earliest dinosaurs, to exploit resources and expand their influence. Top predators such as rhynchosaurs, massive crocodile-line archosaurs, roamed terrestrial landscapes as apex hunters. Equipped with massive skulls lined with serrated blade-like teeth and powerful limbs capable of delivering devastating force, these carnivores specialized in ambush predation and overpowering prey. Their anatomy often favored short bursts of power over sustained pursuit, effectively governing prehistoric riverbanks, forests, and floodplains. Simultaneously, early theropod dinosaurs, though initially smaller, competed as agile predators. Their erect posture, bipedal locomotion, and sharpened sensory organs, especially vision and olfaction, allowed sustained, endurance-based hunting strategies. This enabled them to stalk and chase prey in more open terrains or pursue nimble herbivores like rhynchosaurs and early sauropodomorphs. The prey side of the equation was equally dynamic. Herbivorous reptiles, including rhynchosaurs, aetosaurs, and early sauropodomorphs, employed a mix of defensive strategies, from physical armor, such as the bony osteoderms of aetosaurs, to speed, cryptic coloration, and herd behavior. Their dietary specializations, including tough dental batteries for processing fibrous plants, reflect a coevolutionary response to predator pressures. As predators evolved more efficient hunting techniques, prey species adapted accordingly. Enhanced sensory capabilities, vigilant behaviors, and rapid reproductive cycles characterized many herbivore lineages. The evolutionary arms race extended beyond morphology to encompass behavioral adaptations like territorial defense, escape tactics, and social living. Aquatic and semi-aquatic realms were theaters for similar dynamics. Phytosaurs, crocodile-like semi-aquatic predators with elongated snouts filled with conical teeth, excelled at ambush feeding on fish and smaller vertebrates. Their presence constrained the distribution and behavior of prey species while interacting with terrestrial ecosystems via predator spillover effects along shorelines. Predator-prey dynamics influenced ecosystem structures, energy flow, and species diversity. These interactions promoted trophic cascades, whereby shifts in predator abundance or behavior reverberated through herbivore populations and vegetation communities, occasionally leading to localized extinctions or evolutionary innovations. The fossil record occasionally preserves direct evidence of these interactions. Tooth marks on bones, bite scars, and feeding traces reveal predation or scavenging behaviors, while trackways document pursuit and escape events. Such fossils provide snapshots into the intensity and complexity of ecological relationships shaping the Triassic. Environmental fluctuations, extreme aridity alternated with wet intervals, added layers of complexity. Resource scarcity during droughts intensified competition and predation pressure, pushing species toward flexibility and risk-taking. By contrast, abundant wet periods enabled population booms with consequences for food availability and predator-prey balances. Ultimately, the life and death contest of Triassic ecosystems forged evolutionary pathways characterized by innovation and resilience. The coevolution of predators and prey energized the evolutionary engine driving anatomical and behavioral diversification. This dynamic ecological interplay set the stage for the incredible adaptive radiations that would follow in the Jurassic. As we continue, we will examine how episodic mass extinctions within the Triassic further reshaped these competitions and their profound impacts on the fate of dinosaurs and rival clades. Throughout the Triassic period, life on Earth navigated a landscape marked not only by recovery and diversification, but also punctuated by episodic mass extinction events that profoundly shaped the evolutionary fate of many groups. Unlike the singular cataclysm of the end Permian mass extinction, the Triassic was characterized by multiple environmental crises, each reshaping communities and redirecting ecological trajectories. Understanding these extinctions and their impacts offers crucial insight into how dinosaurs ultimately rose to dominance by capitalizing on the vulnerabilities and declines of their competitors. One of the most notable extinction events within the Triassic is the end Triassic extinction, occurring approximately 201 million years ago. This event is considered one of the Big Five mass extinctions and led to significant losses in marine and terrestrial biodiversity. Volcanic activity associated with the Central Atlantic Magmatic Province, CAMP, released extreme volumes of greenhouse gases, dramatically altering atmospheric chemistry, climate, and oceanic conditions. The ensuing global warming, acid rain, and ocean acidification destabilized ecosystems worldwide. The end Triassic extinction disproportionately impacted many of the dominant crurotarsan lineages, groups of crocodile-line archosaurs such as rhynchosaurs, phytosaurs, and some large predatory species that had ruled terrestrial and aquatic habitats. These formidable reptiles, which had competed vigorously with early dinosaurs, experienced sharp population declines and eventual extirpation in several regions. The loss of such apex competitors created ecological voids. In contrast, dinosaurs, particularly early saurischians and ornithischians, weathered the crisis with comparatively greater success. Their physiological and ecological traits, such as efficient locomotion, metabolic flexibility, and possibly broader dietary niches, likely contributed to their resilience. The post-extinction world thus found dinosaurs increasingly able to occupy niches vacated by their crurotarsan competitors, fueling their rapid evolutionary radiation into apex roles. Other Triassic extinctions, less well-studied but no less significant, also influenced ecosystem restructuring. For example, the Carnian pluvial episode, roughly 234 to 232 million years ago, brought dramatic shifts in climate with increased humidity and rainfall interspersed with harsh environmental stresses. This interval coincides with notable faunal turnovers, including extinctions and radiations of amphibians, reptiles, and plant groups. These climate oscillations imposed fluctuating selective pressures, favoring adaptable lineages and precipitating declines in others. Mass extinctions within the Triassic repeatedly acted as ecological filters, pruning vulnerable taxa and enabling opportunistic and resilient species to expand and diversify. Groups exhibiting generalized feeding behaviors, rapid reproduction, and ecological flexibility tended to persist, while those specialized to narrow ecological roles or constrained physiologies were more prone to extinction. The effects of these mass extinction events extended beyond mere species loss. They reshaped predator-prey dynamics, altered community compositions, and redefined competitive hierarchies. The extinction of numerous dominant predators and herbivores opened niches that dinosaurs and other emerging reptiles exploited, accelerating evolutionary experimentation and diversification. Ecosystem simplification following extinctions also sometimes led to increased ecological instability, but simultaneously provided platforms for innovation. Fossil records from multiple continental exposures illustrate these turnover patterns. The reductions in diversity and abundance of crurotarsan fossils post-end Triassic contrast with the proliferation of dinosaur taxa in early Jurassic strata. Similarly, shifts in plant assemblages reflect ecological opportunities and constraints affecting food sources and habitat structures. Importantly, these extinction episodes underscore that the path to dinosaur dominance was neither linear nor guaranteed. Instead, it involved navigating crises that reshuffled life's hierarchy repeatedly. The ability of dinosaurs to persist and capitalize on these openings speaks to their evolutionary versatility, physiological robustness, and adaptive capacity. In sum, mass extinctions within the Triassic profoundly influenced terrestrial and marine ecosystems, serving as pivotal moments that redefined life's composition and competitive balances. By removing key competitors and restructuring habitats, these events created evolutionary routes that favored dinosaurian expansion. Understanding these dynamics enriches our comprehension of biological resilience and ecological complexity through Earth's deep time. As this story unfolds, we will explore specific fossil cases capturing notable Triassic battles and territorial conflicts, illuminating the tangible evidence of competition, survival, and dominance literally etched in stone. The Triassic period was not only a time of ecological upheaval and evolutionary innovation, but also the stage for literal and figurative turf wars, intense contests over territory, resources, and dominance. These battles between burgeoning dinosaurs and their contemporaries left tangible imprints in the fossil record, offering rare and fascinating glimpses into the interactions that shaped the fate of early reptiles. Studying these paleoecological case studies enriches our understanding of how competition, conflict, and survival instincts played out in the deep past, often documented in the very bones and footprints left behind. One remarkable type of evidence highlighting such ancient competitions is the discovery of fossilized bite marks and combat injuries. For instance, skeletal remains of the early theropod dinosaur Herrerasaurus often bear healed bite marks consistent with intraspecific aggression or predator-prey struggles. Some specimens also show the scars of failed predation attempts by larger Rauisuchians, massive crocodile-line archosaurs, suggesting high-stakes combat for territory or survival. These fossil injuries reveal a world where even the most formidable creatures were participants in life-or-death contests. Trackways provide another compelling record of interactions. At sites like the late Triassic Formation in the southwestern United States, extensive track assemblages show overlapping footprints of coexisting species, including predatory theropods and herbivorous rhynchosaurs, or early ornithischians. Some sequences suggest pursuit or confrontation, where swift carnivores chased nimble herbivores across varied terrain. These traces allow paleontologists to reconstruct potential behavioral scenarios, chase dynamics, escape strategies, and group responses that mirror modern predator-prey interactions. Perhaps the most famous case illustrating Triassic turf wars comes from the Ischigualasto Basin of Argentina, a treasure trove of early dinosaur and archosaur fossils. The co-occurrence of large carnivorous rhynchosaurs and early theropods, like Eoraptor, within the same strata indicates overlapping habitats and resource competition. Fossil assemblages suggest that as rhynchosaurs declined, possibly due to climatic stresses or extinctions, dinosaurs increasingly exploited apex predator niches. In addition to direct confrontations, niche partitioning also served as a subtle form of turf defense, reducing conflict by specialization. Paleoecological analyses of contemporaneous species show differentiation in diet, habitat preference, and activity patterns. For example, aetosaurs occupied armored herbivore niches, while rhynchosaurs primarily grazed on low vegetation, minimizing overlap. Such partitioning tempered aggressive encounters, but also set boundaries for resource use that sparked localized wars when disrupted. Fossilized nests and communal sites contribute complementary insights. Certain early dinosaur nesting grounds reveal tightly packed clutches, indicating territoriality and possibly social cooperation in reproductive defense. Aggressive behaviors likely played roles in protecting these vulnerable areas from rivals or predators, underscoring that competition extended beyond foraging to reproductive success. The interplay of environmental factors further influenced turf wars. Rapid climatic changes during the Triassic caused habitat fragmentation and fluctuations in resource availability, intensifying contests for high-value territories such as water sources, nesting sites, and fertile feeding grounds. Paleo-environmental reconstructions document recurring wet and dry cycles, forcing species into closer contact, heightening conflict intensity. Together, these fossil evidences paint a vivid picture of the Triassic as a period where survival hinged on more than physical prowess. It involved strategic occupation of territory, social negotiation or conflict, and evolutionary innovation in behavior. These ancient turf wars laid the behavioral groundwork for the complex social structures and competitive ecologies observed in later dinosaurs and their contemporaries. Understanding these case studies adds depth to our knowledge of how early dinosaurs not only survived, but thrived amid fierce competition. Their rise was shaped by constant challenges, victories, and losses etched in fossilized bones and footprints, a testament to life's enduring dance between conflict and coexistence. As we proceed, we will explore how this evolutionary arms race extended into other domains, focusing on technological innovations such as teeth, claws, armor, and speed that served as tools for both offense and defense in survival battles of the Triassic. In the vast and fiercely competitive ecosystems of the Triassic period, survival often hinged on possessing the right tools and strategies. What can be thought of as a technological arms race among the planet's early reptiles and other vertebrates. This continual escalation involved the evolution and refinement of morphological features such as teeth, claws, armor, and speed. Each innovation represented a biological technology honed by natural selection that enhanced offense, defense, or mobility, and influenced the balance of power across predator and prey. Understanding this arms race not only illuminates the mechanics of survival, but also offers a window into evolutionary pressures that shaped the future dominance of dinosaurs. Foremost among these adaptations were changes in the dentition of both predators and herbivores. Carnivorous archosaurs developed increasingly specialized teeth, evolving from simple conical shapes to sharply serrated blades, ideal for slicing flesh efficiently. This serration allowed predators like Rauisuchians and theropod dinosaurs to inflict deeper wounds and process their prey more effectively, a decisive advantage in combat and feeding. The gradual differentiation of teeth into incisors, canines, and molariform structures in some lineages reflected dietary specialization and improved processing of varied food types. Herbivores, on the other hand, faced the challenge of breaking down tough, fibrous plant materials dominated by gymnosperms and ferns. Dental batteries emerged as a key innovation. Rows of tightly packed, continuously replaced teeth forming grinding surfaces capable of efficiently shredding vegetation. Rhynchosaurs are a prime example, with their beak-like jaws and repetitive tooth replacement enabling them to exploit an abundant but challenging food source. Later, ornithischian dinosaurs would take this dental complexity even further. Claws, too, became essential instruments in this evolutionary contest. Predators evolved curved, sharp claws suited for grasping and dispatching prey, enabling a more active and manipulative hunting style. Some theropods displayed enlarged killing claws, possibly wielded with precision to incapacitate or kill. For herbivores, claws often served defensive functions, facilitating digging for roots, or even in combat or displays to ward off attackers. Claws thus functioned as multi-purpose tools, enabling survival and reproductive success in varied contexts. Perhaps the most conspicuous adaptation among many Triassic reptiles was the development of body armor. Aetosaurs, with their extensive bony osteoderms forming a protective carapace, stand as a hallmark of this defensive innovation. Such armor provided significant protection against bites and slashes from predators, allowing these herbivores to survive alongside formidable carnivores. This armor sometimes covered virtually the entire body, suggesting that predation pressure was a potent selective force, driving the enhancement of protective structures. The cost of such armor was increased body weight and reduced mobility, a trade-off balanced by other survival strategies like ambush feeding or herd formation. Other armored animals, such as certain crurotarsans and even some early synapsids, developed spikes, plates, or thickened skin regions as additional defenses, illustrating convergent evolutionary solutions to the threat of predation. Speed and locomotor efficiency form another critical dimension of this arms race. The transition of many reptiles to erect postures allowed for more energy-efficient movement and greater stamina. Early theropods, with their elongated hind limbs, digitigrade stance, walking on toes, and lightweight construction, achieved remarkable agility and speed, key to chasing down prey or evading threats. On the prey side, swift herbivorous species developed anatomical adaptations like strong hind limbs and flexible joints to facilitate rapid running and quick directional changes. Agile escape behaviors complemented anatomical speed enhancements, showcasing the interplay of physiology and behavior in predator-prey dynamics. The tail, too, played a vital role in balance and locomotion. Many Triassic reptiles developed stiffened tails with ossified tendons to act as counterbalances during rapid movement, improving agility and stability, critical during high-speed pursuits or evasions. Senses augmented the technological toolkit. Enhanced vision, acute hearing, and olfactory capabilities improved detection of predators or prey, providing invaluable reaction time. Coupled with morphological innovations, these sensory enhancements contributed to the evolutionary success of various groups. This arms race was dynamic and context-dependent, with species continually refining or developing new adaptations in an ongoing cycle of selection and counter-selection. It involved not only direct physical adaptations, but also behavioral strategies such as ambush versus pursuit predation, defensive herding, or even temporal niche partitioning to avoid direct conflict. Crucially, these innovations extended beyond mere survival to influence reproductive success and ecosystem structuring. Well-armed species exerted selective pressures on others, leading to co-evolutionary trajectories that built increasingly complex ecological communities. In conclusion, the technological arms race of teeth, claws, armor, and speed during the Triassic was a defining facet of vertebrate evolution. It reflects the intricate balance of offense, defense, and agility sculpted by environmental challenges and interspecies competition. These evolutionary battles set the foundational adaptations for many Mesozoic lineages, including the dinosaurs, enabling them to thrive and dominate in the ages to come. Next, we will explore how reproductive strategies, especially the role of eggs and nesting behaviors, further contributed to dinosaur success, complementing their physical adaptations with life history innovations. Reproduction, an essential driver of biological continuity and evolutionary success, took on distinctive forms in the dawning age of dinosaurs, and its innovations significantly contributed to their ascendancy during the Triassic period. The role of eggs and associated reproductive strategies in the survival and proliferation of dinosaurs offers a profound window into how life history traits intersected with anatomy, ecology, and environmental pressures, ultimately influencing dinosaurian dominance for millions of years. Unlike many aquatic ancestors that released eggs into water, early reptiles evolved oviparity, that is, laying eggs with protective shells in terrestrial habitats. Dinosaur eggs, composed primarily of a calcareous shell similar in mineralogy to modern birds' eggs, presented crucial advantages. The hardened eggshells provided mechanical protection against predators, desiccation, and temperature fluctuations, factors that were especially vital in the often harsh and highly variable Triassic environments. This adaptation allowed dinosaurs to colonize diverse terrestrial niches, including arid or seasonally dry regions, where softer-shelled eggs and aquatic reproduction would not have been viable. Dinosaur eggs exhibit an astonishing diversity in size, shape, and microstructure, reflecting evolutionary experimentation and species-specific reproductive strategies. Early dinosaur eggs were often spherical to ellipsoidal, variable in size but generally relatively small compared to those of later giant sauropods. The porosity and thickness of the shells influenced gas exchange and water permeability, balancing embryo development needs with environmental challenges. Fossilized nesting sites discovered worldwide reveal complex reproductive behaviors extending beyond simple egg-laying. Clutches of eggs arranged in organized patterns indicate deliberate nesting, perhaps in communal sites or with repeated use of suitable locations. Such nesting behavior would have enhanced reproductive success by providing stable incubation environments, protection from environmental extremes, and reduced predation risks. Evidence for brooding behaviors, wherein adults guard or thermally regulate nests, although better documented in later dinosaur groups, may trace roots to some Triassic species. These behaviors represent a transition toward enhanced parental investment, increasing offspring survival possibilities and influencing social structures. Reproductive strategies also encompass clutch sizes and frequency. Early dinosaurs likely balanced producing multiple offspring with sufficient parental care to ensure survivability. A larger clutch size could offset high juvenile mortality, common in turbulent Triassic ecosystems, aiding population persistence and genetic diversity maintenance. Egg size and developmental strategies intertwined with life history evolution. Some dinosaurs exhibited rapid growth rates in juveniles, supported by the need to quickly reach sizes less vulnerable to predation. This accelerated growth was made possible by efficient incubation and well-protected early developmental stages within eggs. Additionally, variation in reproductive timing, possibly linked to seasonal environmental fluctuations, suggests that dinosaurs adapted their breeding cycles to optimize resource availability and juvenile survival chances. The ability to modulate reproductive behavior in response to climatic and ecological pressures was critical in the face of Triassic's environmental extremes. The fossil record of dinosaur embryos and hatchlings, although fragmentary, helps reconstruct developmental stages and physiological traits. It reveals that reptiles of this period had relatively advanced embryonic development and metabolic rates, supporting hypotheses of high growth and activity levels in young dinosaurs. Reproductive adaptations also played roles in dispersal and biogeography. The hard-shelled eggs permitted species to exploit new territories with diverse climates and ecologies across the vast supercontinent Pangaea. Such dispersal capacity contributed to the geographic radiation of dinosaur lineages. Importantly, reproductive success in dinosaurs was deeply integrated with anatomical and behavioral innovations. The freeing of forelimbs via bipedalism, social behaviors like territoriality and cohabitation, and enhanced sensory capacities all contributed to complex reproductive ecologies. In sum, the evolution of eggs and reproductive strategies was not a mere background process, but a central engine driving dinosaur success. Protective eggshells, nesting behaviors, potential parental care, and flexible reproductive timing created conditions conducive to survival in challenging environments and fostered population stability and expansion. As the Triassic period unfolded, these reproductive advantages, combined with anatomical and ecological innovations, allowed dinosaurs to establish and expand populations resiliently, setting the stage for their unparalleled Mesozoic reign. Understanding this facet enriches our appreciation of how life history intricately weaves into the fabric of evolutionary triumph. Looking forward, we will examine how these reproductive strategies intersected with the global distribution of dinosaurs, influenced by continental drift and shifting habitats, further expanding their reach across ancient Earth. The global distribution of dinosaurs and their early relatives during the Triassic period was profoundly influenced by the dynamic geological processes shaping Earth's surface, most notably the slow but relentless drift of continents. This continental drift not only reconfigured land masses, but also dictated the dispersal pathways, habitat availability, climatic zones, and ecological opportunities that ultimately facilitated dinosaur expansion and diversification across the ancient supercontinent Pangaea and beyond. In the Triassic, roughly 252 to 201 million years ago, all major land masses were fused into a singular, vast supercontinent known as Pangaea. This enormous landmass stretched from the northern to the southern poles, encompassing a tremendous latitudinal gradient and a variety of climatic zones, from arid interior deserts to more temperate and humid coastal regions. The central positioning within Pangaea, however, meant large inland areas experienced harsh seasonal extremes, including intense heat and prolonged dryness, challenging the survival and dispersal of terrestrial fauna. Early dinosaurs and their close archosaur relatives first evolved within specific refugia, or localized habitats, where conditions favored their persistence. Fossil evidence reveals that the earliest dinosaurs emerged primarily in parts of present-day South America, particularly in the Ischigualasto and Los Colorados formations of Argentina. These areas provided rich sedimentary contexts, preserving a diverse assemblage of early dinos and contemporaneous archosaurs, indicating flourishing ecosystems under seasonal climates. The broad, contiguous landmass of Pangaea offered an unparalleled avenue for biotic interchange, permitting dinosaurs to disperse across vast distances over time. Unlike today's fragmented continents that create geographic barriers and isolate populations, the connectedness of Triassic Pangaea facilitated gene flow, migration, and adaptive radiation. Dinosaurs could exploit diverse regional ecosystems, from lowland floodplains and river valleys to upland forests and coastal margins. Progressive continental drift began to subtly modify these landscapes as the initial breakup of Pangaea commenced near the late Triassic. These tectonic movements initiated the opening of proto-oceans such as the Central Atlantic, leading to the gradual formation of distinct continental fragments. These geographical changes introduced emerging barriers, climate heterogeneity, and isolated habitats, which in turn promoted allopatric speciation, the formation of new species due to population separation. For dinosaurs, this evolutionary driver magnified diversity and specialization across emerging provinces. Moreover, variations in climate linked to continental positioning heavily influenced the distribution patterns of dinosaur taxa. For example, the wet and humid zones along Pangaea's western coastal margins fostered lush plant communities, supporting diverse herbivorous dinosaurs, whereas interior arid zones selected for species adapted to xeric conditions. This environmental gradient encouraged niche partitioning and regional diversification. Fossil discoveries from regions beyond South America attest to the geographic spread of dinosaurs by the late Triassic. Triassic dinosaur fossils have been found across present-day North America, Europe, Africa, and Asia, illustrating their broad dispersion and ecological success. In North America's Chinle Formation, for example, remains of early theropods and herbivores coexist with other archosaur lineages, showing cohabitation and competition across Pangaea's northern sectors. Some dinosaur groups even exploited island chains and varied paleogeographic features created by sea level changes and tectonics. These fragmented habitats offered novel ecological opportunities and refuges from competitors and predators, facilitating adaptive innovation and speciation. Continental drift also influenced preserving conditions, affecting the quality and distribution of the fossil record that modern science relies on. Regions where sedimentary basins accumulated thick layers favored fossilization and detailed stratigraphic framework, allowing paleontologists to decode patterns of dinosaur expansion and diversity with increasing resolution. It is crucial to appreciate that continental drift did not act in isolation, but intersected with climate shifts, ecological interactions, and extinction events. Synergistic effects sculpted dinosaur biogeography, with glacial and interglacial cycles, volcanic activity, and oceanic circulation patterns further complicating the distribution landscape. Ultimately, the vast, connected realm of Triassic Pangaea combined with evolving topography and climate to create a complex matrix through which dinosaurs expanded. Their ability to adapt to diverse ecosystems, traverse vast distances, and diversify into myriad forms reflects this intricate geological and environmental tapestry. The global distribution and spread of dinosaurs during the Triassic set the stage for their spectacular radiation in the Jurassic and Cretaceous. Their evolutionary and ecological flexibility, coupled with geological opportunity, forged a success story intimately linked to the restless movements of Earth's crust. As we proceed, the narrative will focus on the late Triassic fauna, highlighting how apex dinosaurs began to emerge and consolidate their dominance within these expanding terrestrial realms, forever altering Earth's biological landscape. As the Triassic period unfolded into its later stages, Earth's ecosystems grew increasingly complex and dynamic, setting the stage for a pivotal evolutionary transition. The emergence of apex dinosaurs. The late Triassic, spanning roughly from 237 to 201 million years ago, was a remarkable epoch. It was during this period that dinosaurs moved beyond their humble beginnings, rising as dominant vertebrates in terrestrial habitats and hinting at the spectacular Mesozoic reign that lay ahead. To fully grasp this transformation, we delve into the late Triassic fauna, unveiling the ecological context, key players, and evolutionary processes that facilitated the ascent of apex dinosaurs. The late Triassic world was a rich tapestry woven from the threads of both archaic survivors and rapidly diversifying lineages. Foremost among the dominant reptiles were the crurotarsans, or crocodile-line archosaurs, which included enormous predators such as rhynchosaurs. These massive quadrupedal carnivores boasted formidable skulls with serrated teeth and stout limbs, making them powerful apex predators in many late Triassic ecosystems. They occupied a wide range of terrestrial and semi-aquatic habitats, rivaling early dinosaurs for ecological supremacy. Yet, in this realm of titanic reptiles, dinosaurs began to carve out a niche for themselves, increasingly appearing in paleontological sites as significant components of late Triassic faunas. Early theropods, such as Coelophysis, from the southwestern United States exemplify this trend. Relatively small but swift, bipedal, and armed with sharp teeth and claws, these predators were adapted for endurance and agility, traits granting them distinct advantages in hunting and survival. Simultaneously, herbivorous dinosaurs, early sauropodomorphs and ornithischians, started exploiting diverse plant resources. These early herbivores displayed a mix of bipedal and quadrupedal stances and developed more complex dentition suited for processing increasingly tough vegetation dominated by gymnosperms, like conifers and cycads. Their expanding populations altered plant communities and formed a crucial link in terrestrial food webs. Late Triassic assemblages reveal a mosaic of species where dinosaurs and crurotarsans coexisted, sometimes competing directly for food, territory, and reproductive opportunities. However, evidence suggests that the evolutionary flexibility of dinosaurs, their bipedal locomotion, variable diet, likely higher metabolic efficiency, and reproductive strategies, enabled them to exploit niches inaccessible or less efficiently used by many crurotarsans. Moreover, the late Triassic witnessed significant environmental changes, including shifts toward drier climates punctuated by episodic wetter intervals, which played a role in reshaping faunal dominance. Dinosaurs' adaptive traits better suited them to survive and spread through such fluctuating conditions. Fossil records from the Ishigualasto Formation, the Chinle Group, and European basins unveil a dynamic interplay. Morphologies, diversity, specimens of various sizes and ecological roles, and traces of predator-prey interactions underscore an escalating evolutionary arms race. These interactions drove faster evolutionary rates and complex community structures. Notably, large herbivorous aetosaurs and rhynchosaurs, armored with bony plates, declined toward the late Triassic's close, possibly due to climatic stress and competition. Their waning coincided with the gradual increase of dinosaurian herbivores, marking a faunal turnover that presaged the dinosaur-dominated Jurassic. In this critical window, dinosaurs steadily climbed trophic ladders, with some species growing larger, occupying apex predator roles. Theropods like Tropostasuchus, otuor-sized Chohererasaurus illustrate this shift. Also, herbivores evolved more efficient feeding mechanisms, enabling higher biomass support and influencing ecosystem productivity. Thus, the late Triassic was not simply a transitional epoch, but an arena where dinosaurs began to assert dominance, a complex evolutionary dance choreographed by competition, environmental change, and innovation. This era foreshadowed the Mesozoic's grand dinosaurian drama, with survival strategies and ecological adaptations that would propel dinosaurs to unmatched terrestrial reign. As we continue, we will explore the auxiliary groups that survived alongside these emerging dinosaurs, such as mammal-like reptiles and amphibians, whose fortunes waxed and waned amid the shifting landscapes of the Triassic. As the Triassic period played out amidst the backdrop of environmental upheavals and evolutionary innovation, it was not only dinosaurs and archosaurs that shaped the terrestrial landscapes. Other lineages, including mammal-like reptiles and amphibians, also persisted into this era, though their fates varied greatly. These survivors, vestiges of ancient ecosystems, provide crucial insight into the complexity of the Triassic biosphere and illuminate the evolutionary narratives that accompanied the dinosaurs' rise. Mammal-like reptiles, also called synapsids, represent a group that dominated Permian terrestrial ecosystems before the Great Dying. These iconic creatures included diverse forms, from the saber-toothed gorgonopsians to the herbivorous dicynodonts, many of which were large-bodied and ecologically significant. However, the mass extinction at the end of the Permian decimated their diversity and reduced their ecological dominance. In the Triassic, mammal-like reptiles lingered but in progressively diminished roles. Small, more specialized forms survived, often adapting to niches that allowed them to avoid direct competition with the increasingly prominent archosaurs and early dinosaurs. Some cynodonts, the lineage closest to mammals, displayed evolutionary innovations, such as more efficient jaws, complex teeth, and metabolic improvements. Over time, these traits laid the groundwork for the rise of true mammals, but during the Triassic, most synapsids were still minor players overshadowed by the archosaur ascendancy. Amphibians also persisted through the Triassic, though their diversity was curtailed relative to the Permian. Large temnospondyle amphibians survived in moist environments, particularly in riverine or lacustrine habitats. These creatures often retained primitive features and filled analogous ecological roles to those of modern crocodiles, including ambush predation in aquatic settings. The Triassic amphibians faced challenges from drying climates and shifting habitats brought about by continental configurations and climate cycles. These environmental pressures, coupled with competition from adept reptiles, restricted their range and numbers. Nevertheless, some amphibian groups flourished in localized refuges, demonstrating resilience amid adverse conditions. Fossil evidence paints a picture of gradual decline for many of these other survivors. While mammal-like reptiles gradually shrank in size and ecological influence, early mammals began emerging toward the late Triassic, typically small and nocturnal, potentially taking advantage of niche openings less accessible to daytime active reptiles. Amphibians' continued, albeit reduced, presence in wet habitats suggests a scenario of ecological fragmentation, where environmental changes partitioned species into scattered populations of varying success. Many amphibians likely played key roles in nutrient cycling and food chains within aquatic ecosystems. This shifting ecological landscape illustrates a broader evolutionary principle. Survival following mass extinctions is less about maintaining former dominance and more about adaptability, flexibility, and filling new or altered roles. Mammal-like reptiles and amphibians exemplify lineages that, while diminished, acted as evolutionary bridges to later faunas. The transition of dominance from synapsids and amphibians to archosaurs and dinosaurs was neither instantaneous nor absolute. Instead, it was a gradual, complex process marked by competition, coexistence, and environmental filtering. Studying these survivors offers perspective on the broader dynamics of resilience and innovation during Earth's transformative Triassic period. Understanding the fates of these groups enriches our comprehension of the evolutionary stage on which dinosaurs rose to prominence and highlights the intricate tapestry of life, painted with both endurance and extinction, that characterized the dawn of the Mesozoic era. Next, we'll delve into a fascinating climatic episode, the Carnian pluvial episode, and its substantial impact on populations and ecosystems, further shaping the evolutionary trajectories of dinosaurs and their contemporaries. The Carnian pluvial episode, CPE, occurring approximately 234 to 232 million years ago during the late Triassic, stands as one of the most significant climatic and ecological events of the Mesozoic era, a dramatic interval marked by pulsating wet climates that temporarily reversed the overarching arid conditions dominant across much of Pangaea. This episode of intensified rainfall and humidity profoundly influenced global ecosystems, triggering population booms, faunal turnovers, and evolutionary radiations that left lasting imprints on the biosphere. To appreciate the rise of the dinosaurs and the restructuring of life during this critical juncture, it's essential to explore the causes, impacts, and consequences of the Carnian pluvial episode. The atmospheric and geological drivers of the CPE appear linked to tectonic and volcanic activity, possibly associated with renewed phases of the Central Atlantic magmatic province eruptions. These volcanic events released copious greenhouse gases and aerosols, leading to instability in climate systems, alterations in oceanic circulation, and increased precipitation. Paleoclimatic proxies, including sedimentary records, oxygen isotope data, and palynological evidence, reveal a marked shift from previously dry to markedly wetter conditions globally. This climatic wet phase dramatically altered vegetation patterns. Expanded rainforests and lush fern-dominated understories replaced extensive arid landscapes, providing abundant and diverse plant biomass. Such increased primary productivity set the stage for trophic cascades throughout terrestrial ecosystems. Herbivorous vertebrates, previously limited by resource scarcity, found themselves in an environment capable of sustaining larger populations and greater species richness. Consequently, the fossil record indicates notable population booms among herbivorous reptilian groups, including rhynchosaurs, early sauropodomorph dinosaurs, and other archosaurs. These herbivores exploited the expanding vegetation, benefiting from the increased availability of food resources. Their dietary expansion likely encouraged diversification in feeding apparatus and digestive strategies, feeding into a feedback loop of ecological complexity. Carnivorous predators responded in kind to these herbivore surges. Theropod dinosaurs and large crurotarsans increased in number and variety, capitalizing on abundant prey and driving selective pressures that enhanced hunting adaptations. This proliferation of both herbivores and carnivores generated new predator-prey dynamics, further stimulating evolutionary innovation. Marine ecosystems also experienced significant shifts during the CPE. Reefs flourished anew, and diverse marine invertebrates, ammonoids, and fish populations expanded, paralleling terrestrial trends. The interconnectedness of land and sea was emphasized through altering sedimentation patterns, nutrient fluxes, and faunal exchanges. While the CPE promoted biodiversity and population expansions, it also heralded substantial faunal turnovers. Some archaic taxa declined or vanished amidst changing habitats and competition pressures, notably certain amphibians, dicynodonts, and non-archosaurian reptiles. These dynamic turnovers paved the way for newer lineages, including dinosaurs, to occupy newly available ecological landscapes. Localized extinctions and biotic replacements associated with the Carnian pluvial episode serve as ecological reset buttons that instigated evolutionary radiations. The disruptive yet opportunistic nature of these environmental shifts exemplifies how climate can serve as both a selective agent and a facilitator of biodiversity. Moreover, the CPE's impact on population dynamics reflects the inherent complexity of ecosystem resilience. Rapid expansions were often followed by contractions, reflecting the oscillating environmental conditions and competing biotic interactions. This ebb and flow underscored the adaptive challenges early vertebrates faced, demanding flexibility in life history traits and behaviors. The legacy of the Carnian pluvial episode lies not merely in immediate biotic changes, but in setting evolutionary trajectories that culminated in the dominance of dinosaurs and the restructuring of Mesozoic ecosystems. By fostering population booms and facilitating evolutionary innovations, the CPE functioned as a crucible within which selection pressures intensified and life's diversity blossomed anew. In the ensuing sections, we will explore how these climatic and ecological shifts culminated in the final competitions among vertebrate groups, heralding the gradual demise of many Triassic rivals and the eventual unrivaled dominance of dinosaurs in the dawn of the Jurassic. As the Triassic period neared its close, Earth's terrestrial ecosystems were embroiled in intense competition and rapid transformation. The stage was set for a decisive evolutionary showdown where the emerging dinosaurs and their reptilian rivals clashed in a final contest for dominance. This epoch was characterized by an intricate interplay of biological innovation, environmental pressures, and extinction events that ultimately tipped the scales in favor of the dinosaurs, setting them on a path to unchallenged supremacy in the Jurassic and beyond. Several groups that had once held significant sway in Triassic ecosystems, including the formidable cruising crurotarsans such as Rauisuchians and the well-armored aetosaurs, found their fortunes declining. These archosaurian contemporaries of dinosaurs faced mounting challenges due to a combination of ecological competition, climatic fluctuations, and episodic extinction pulses. The dynamic landscapes fluctuating between aridity and humidity alongside volcanic episodes exerted relentless selective pressures that some lineages could not withstand. Dinosaurs, leveraging their anatomical adaptations, such as erect limb posture conducive to efficient locomotion, bipedalism affording agility and freeing forelimbs for manipulation, and possibly enhanced respiratory systems, exploited niches increasingly vacated by faltering competitors. Their diverse feeding strategies allowed them to capitalize on the aerobic expansion of gymnospermous vegetation, marked by high resilience and adaptability. Additionally, reproductive advantages through protective eggshells, nesting behavior, and potential parental care increased dinosaurian offspring survival rates relative to many rivals. These factors combined to foster population expansions and enhanced genetic diversity, key drivers of adaptability. A pivotal agent facilitating this evolutionary shift was the series of late Triassic extinction events, especially the end Triassic mass extinction. Triggered by massive flood basalt volcanism in the central Atlantic magmatic province, these events caused environmental upheavals, ranging from global warming and ocean acidification to habitat disruption, that severely impacted many crurotarsan lineages. Meanwhile, dinosaurs exhibited greater resilience, likely owing to their physiological and ecological flexibility. As competitors' numbers dwindled, dinosaur lineages radiated into vacated apex herbivore and predator roles. Large theropods began commanding predatory niches, while sauropodomorphs evolved toward gigantic sizes, exploiting abundant plant biomass. This competitive drama also entailed localized turf wars, where territorial behavior and social dynamics determined access to critical resources. Fossil evidence of bite marks, healed injuries, and overlapping trackways suggests active interspecific conflicts. The waning of mammal-like reptiles, many amphibians, and other archaic vertebrates further accentuated the reshaping ecological hierarchy. Dinosaurs capitalized on these shifts by adjusting life history strategies, ranging from social cooperation to temporal niche partitioning. Thus, the Triassic's final act was not a sudden takeover, but an intricate process involving incremental gains, persistent contest, and opportunistic exploitation. The selective pressures and ecological upheavals forged an evolutionary crucible wherein dinosaurs evolved from marginal players to dominant clades. Recognizing these competitive transitions enriches our understanding of the profound adaptability and innovation embodied by early dinosaurs, qualities that enabled them to thrive amid adversity and transform the evolutionary trajectory of life on Earth. In the following section, we explore the dawn of the Jurassic period, where dinosaurs seized uncontested dominance and unleashed one of the most spectacular evolutionary radiations in Earth's history, becoming truly unstoppable forces of nature. As the Triassic period drew to a close approximately 201 million years ago, Earth underwent a profound transformation that set the stage for a new era, the Jurassic. This pivotal boundary marks not only a geological transition, but also an evolutionary watershed during which dinosaurs, once a modest and somewhat marginal group, rose to fill virtually every ecological niche, emerging as the undisputed rulers of terrestrial ecosystems. The dawn of the Jurassic reveals a remarkable story of persistence, adaptability, and innovation, a chapter where dinosaurs became truly unstoppable. The catalyst for this monumental shift was the end Triassic mass extinction, a global event triggered by intense volcanic activity associated with the Central Atlantic Magmatic Province, CAMP. Massive flood basalt eruptions unleashed unprecedented volumes of greenhouse gases, including carbon dioxide and methane, which precipitated rapid climate warming, acid rain, and widespread ocean acidification. These environmental upheavals led to the decline or extinction of numerous vertebrate groups that had competed with dinosaurs throughout the Triassic, most notably the dominant crocodile line archosaurs, Rauisuchians, phytosaurs, and aetosaurs. Dinosaurs, however, displayed remarkable resilience and adaptability amid these catastrophic changes. Their anatomical innovations, such as erect limbs for efficient locomotion, bipedalism enhancing their agility, effective respiratory systems supporting high metabolic rates, and sophisticated reproductive strategies, conferred distinct advantages. Coupled with flexible diets and the ability to exploit a wide range of habitats, these traits facilitated their survival when many competitors fell. With the decline of rival lineages, dinosaurs rapidly expanded into vacated ecological roles. Early Jurassic strata reveal a profusion of diverse dinosaur species occupying apex predator roles, herbivore niches, and everything in between. Theropods, such as Dilophosaurus, evolved larger sizes and more refined hunting adaptations. Sauropodomorphs, the ancestors of the gigantic long-necked sauropods, began their steady increase in body size, enabling access to high foliage and secure resource exploitation. This explosive radiation was not limited to sheer abundance, but involved extensive morphological, ecological, and behavioral diversification. Dinosaurs evolved novel feeding strategies, social behaviors, and habitat specializations, contributing to their ecological versatility and colonization of lands worldwide. The continental breakup initiated in the late Triassic further facilitated this diversification by decentralizing populations and fostering allopatric speciation. The Jurassic fossil record across North America, Europe, Asia, and Africa paints a vivid picture of sprawling dinosaur-dominated ecosystems, with lush forests, expansive floodplains, and meandering rivers supporting complex food webs. Dinosaurs became the key architects of these systems, exerting top-down ecological control as herbivore grazers modulated plant communities and carnivores influenced herbivore populations. Importantly, the rise of dinosaurs ignited broader evolutionary cascades. Their dominance reshaped the fate of other vertebrate groups, including mammal-like reptiles and amphibians, many of which shifted to smaller, more secretive niches. The proliferation of dinosaur eggs and nesting behaviors also introduced new dynamics in reproductive ecology and life history. The dawn of the Jurassic also witnessed integration with marine and aerial ecosystems. The radiation of marine reptiles and the emergence of the first birds from theropod dinosaurs illustrate the expansive reach of dinosaurian evolutionary influence. Thus, the transition from Triassic to Jurassic signifies more than a temporal boundary. It marks the ascendancy of a lineage that transformed Earth's biological narrative. Dinosaurs' rise from resilient survivors to ecological superstars demonstrates the power of adaptability, innovation, and opportunism amid adversity. As this saga continues, the final sections will reflect on the lessons gleaned from the Triassic's crucible. Lessons about survival, creativity, and the dynamic interplay between life and environment that resonate well into the story of life on our planet today. The Triassic period serves as a profound chapter in Earth's evolutionary history, an era marked by devastation and renewal, challenge and triumph, laying the groundwork for the supremacy of dinosaurs and the unfolding drama of the Mesozoic. Reflecting on this distant past uncovers enduring lessons about adaptability, innovation, and survival that resonate even in today's dynamic world. First and foremost, the Triassic illustrates life's remarkable resilience. Emerging from the harsh crucible of the Permian-Triassic mass extinction, the most severe denouement of biodiversity, the biosphere did not merely recover, it transformed. Species that persisted did so by embracing adaptive flexibility, evolving novel morphologies, physiologies, and behaviors suited to fluctuating and often extreme environmental conditions. This resilience teaches us that survival often favors versatility and responsiveness to change rather than rigid specialization. Innovation, both anatomical and behavioral, was a hallmark of the Triassic biotic rebound. The evolutionary experiments of early reptiles, ranging from limb posture modifications enabling erect stances, the development of bipedal locomotion, specialized teeth and jaws for diversified diets, to reproductive adaptations such as protective eggs and social nesting, demonstrate that success in life is often predicated on breaking from established norms and venturing into new functional realms. These innovations not only allowed organisms to fill newly available ecological niches, but also generated dynamic evolutionary feedback loops, fostering further diversification. Competition and ecological interactions during the Triassic underscored the importance of continual adaptation. The arms races between predators and prey accelerated morphological and behavioral refinements that led to greater complexity in ecosystems. Social behaviors like territoriality and community formation reveal that survival depended not only on individual capabilities, but also on cooperation, communication, and structured interactions within populations. Environmental pressures, particularly the chaotic climates and episodic mass extinctions characteristic of the Triassic, highlight the integral role of external forces in shaping life's trajectory. The Carnian pluvial episodes' wet intervals spurred population booms and diversification, while climatic extremes tested physiological and ecological limits. These patterns underscore the interconnectedness of Earth's systems and the contingency of life on delicate balances. The gradual rise and dominance of dinosaurs were not the product of chance alone, but the culmination of relentless evolutionary processes, survival of the fittest in its broadest sense, encompassing adaptability, innovation, and opportunism. Their journey from modest beginnings to Mesozoic rulers exemplifies how persistence combined with evolutionary creativity can unlock unprecedented ecological success. These lessons from the Triassic are timeless. In an era of unprecedented global change, understanding life's past resilience and adaptiveness offers both inspiration and caution. It reminds us that evolutionary and ecological systems are dynamic, ever-changing, and that flexibility and innovation remain vital ingredients for survival in the face of uncertainty. As we close this journey through the Triassic, we celebrate the indomitable spirit of life, a grand narrative of survival and transformation that continues to unfold. The story of the early dinosaurs and their contemporaries is a testament to the power of evolution, offering insights into our own world and its future possibilities.